Somewhere out there, gravity has grown so absolute it doesn't just swallow stars, it edits time and seals off a universe behind a one-way edge. It's not a monster you can see, it's a boundary you can't cross. So what is the biggest black hole we can meaningfully talk about? And what does finding it do to everything we think we know about reality? A black hole can outweigh entire galaxies' worth of stars and still fit inside a region smaller than our solar system. In its vicinity, distance becomes a kind of clock, and light itself starts keeping in perfect time. In this film, we follow the largest black holes as a trail of evidence, etched into starlight, radio waves, and the restless glare of quasars. Biggest sounds simple until you try to define it in a universe that measures mass, size, and influence differently. Is the true champion the one with the most mass, the widest horizon, or the farthest reach into its host galaxy? And if our instruments never touch the object itself, what does it mean to claim certainty at the edge of the measurable? Every number we quote is a verdict delivered by motion, by spectra, by timing, and by models that can mislead. We will begin by dismantling the familiar cartoon of black holes as cosmic vacuum cleaners. Far from the centre, gravity behaves with calm predictability. An orbit does not care whether the mass is a star or a horizon. Then the story turns, and gravity stops acting like a pull through space, because in Einstein's universe, it becomes the shape of space. We will build an intuition for horizons not as surfaces you strike, but as boundaries drawn in the future. To reach the giants, we have to ask how nature grows them at all. We will trace a lineage from collapsing stars to galactic nuclei, and then into the early universe where time is scarce. There, the record books become a battlefield of method and uncertainty. We will learn how astronomers weigh something invisible by watching what it makes other things do, and why the largest claims are also the most fragile. Our expedition then locks onto a famous contender, TON 618, a quasar whose light has travelled billions of years to reach us. It arrives not as a photograph, but as a coded report. Broad lines, shifting colours, and flickers that hint at scale. But this journey is not only a chase for a number. As we approach the horizon in imagination and in mathematics, we meet the deeper stakes, information, irreversibility, and the uneasy coexistence of relativity with quantum law. By the end, the question is no longer which black hole is merely the largest. It is what largest can responsibly mean, and what these objects force us to admit about time, geometry, and the limits of explanation. The universe will not hand us a single trophy and a clean ending, only clues, constraints, and a frontier that keeps moving outward as we learn to see. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From the myths that surround black holes to the measurements that define them, each chapter tightens the search while widening the implications. And when a candidate finally towers above the rest, we will ask what its enormity makes possible and what it forbids. The sky looks calm, but calm is not the same as simple. In a wide, quiet star field, there can be a region where time refuses to keep our pace. Light can enter, but it cannot return with news. The universe holds places that look almost empty, yet their consequences are absolute. We call them black holes, and popular stories call them cosmic vacuums. The vacuum myth says they roam and swallow, pulling everything nearby into darkness. That picture is easy to remember, and mostly wrong. A black hole is not defined by appetite, or even by what it contains. It is defined by a boundary in space-time geometry that changes what can happen next. General relativity did not invent black holes as monsters. It predicted them as clean solutions to equations about gravity and motion. When mass and energy curve space-time enough, paths that once led outward stop existing. The result is not a mouth, but a map with a missing direction. The unsettling part is that the math is accessible, while the interior is not. Historically, the idea arrived before the name. In the 18th century, thinkers like John Michel and Pierre-Simon Laplace imagined dark stars, whose gravity could trap light. Their reasoning used Newton's gravity, and an early concept of light as particles. Einstein's relativity later replaced that picture with geometry, space and time themselves becoming the trap. This chapter begins with that contradiction. Black holes are mathematically inevitable in Einstein's framework, yet physically inaccessible by any signal we can receive. We can orbit them, measure them, and watch matter heat as it falls. We cannot look past the boundary and report back. The story is a mystery built from precise rules. The key rule is the event horizon. The horizon is not a surface you could touch like rock or ice. It is a causal boundary, a one-way membrane for information. Cross it, and every future path points inward, even for light. Outside it, the universe still has options. To visualize that boundary, imagine a river that speeds up as it approaches a waterfall. Far upstream, you can paddle against the current and return. Closer in, the flow becomes too strong for any boat to escape. At the horizon, even light, nature's fastest messenger, cannot fight its way back upstream. That definition matters because it separates the black hole from its surroundings. The bright whirl of an accretion disk is not the black hole. The disk is ordinary matter, heated by friction and gravity, radiating before it crosses the horizon. Jets are not the black hole either, even when they span galaxies. They're powered by magnetic fields and rotating plasma near the boundary. In visuals, the difference is stark. The disk can glow white-blue with X-rays, while dust lanes cut dark arcs across the frame. Magnetic field lines twist like invisible cables threading the inner disk. Then, from the poles, narrow beams lance outward, jets that look like searchlights across intergalactic space. The singularity is a different idea, and it is often misused. In the simplest equations, density rises without limit at the center. That point is not an observed object, and it may not be physical as described. It signals that our current theory is incomplete at extreme scales. The horizon, by contrast, is a real prediction about what observers can and cannot exchange. In relativity, a singularity is often a warning label in the mathematics. It tells us that curvature becomes so extreme that the equations stop behaving. Many physicists expect quantum effects to intervene at that scale, reshaping the interior description. Whatever the final answer is, it must still respect the horizon's role as an information boundary. The vacuum myth also fails for a simpler reason. Black holes do not suck more than anything else with the same mass. Far from the horizon, gravity depends on total mass and distance, not on whether the mass is a star or a black hole. Replace the Sun with a black hole of equal mass, and Earth would keep orbiting. The danger comes from getting close, not from a special pulling power. Orbital dynamics explain why. Objects in space usually have angular momentum, and angular momentum resists straight inward fall. Planets, gas clouds, and stars move on paths set by energy and momentum. To spiral inward, they must lose energy, often through friction, collisions, or radiation. Black holes capture what comes near, but they do not reach out like nets. This is why accretion disks form. Infalling gas rarely drops straight down, because it carries sideways motion from its past. It circles, collides, heats, and slowly sheds angular momentum. Only then does it cross the horizon, and that crossing is silent to the outside. The disk can blaze while the horizon remains dark. The heating is not a vague glow, but a measurable conversion of gravitational potential energy. As gas spirals inward, it is sheared into layers moving at different speeds. Turbulence and magnetic instabilities stir it, turning ordered motion into heat. That heat radiates across the spectrum, from optical light to hard X-rays. So what are we really seeing when we see a black hole? We see effects, not interiors. We measure the motion of nearby stars and gas. We measure the spectrum of hot matter as it spirals inward. We measure shadows and rings shaped by extreme lensing. The object is defined by what it forbids, and we infer it by what it allows. Even the famous shadow is not the horizon itself. It is a silhouette created by light paths that are bent, trapped, and redirected. Photons can orbit briefly on unstable trajectories near the photon sphere, piling brightness into a thin ring. The darkness in the center is a deficit of escaping light, not a painted black surface. That brings us to the documentary's quest. We are traveling in evidence and in imagination toward the biggest black hole in space. But biggest is not one simple number. It can mean the greatest mass, the largest horizon radius, or the widest gravitational influence. It can mean the most energy output through accretion, even if the hole itself stays dark. Mass is the most common yardstick because it sets the scale of everything else. For black holes, horizon size grows roughly in direct proportion to mass. A more massive hole has a larger Schwarzschild radius, and a gentler tidal gradient at the horizon. Paradoxically, the biggest holes can be easier to cross without immediate spaghettification. The trap is deeper, but the edge can feel calm. This calmness has a geometric reason. Tidal forces depend on how quickly gravity changes with distance. For a supermassive black hole, the horizon is so large that the gradient can be mild at the boundary. The fatal stretching may wait until far inside, beyond any chance of sending a warning outward. Influence is another meaning of biggest, and it is easy to confuse. A supermassive black hole can dominate the inner region of a galaxy, shaping stellar orbits and feeding active nuclei. Yet its influence has a boundary of its own, where the galaxy's mass takes over. A smaller hole in a sparse environment can have a cleaner sphere of control. Biggest depends on what you measure and where you stand. In a crowded galactic core, gravity is a chorus, not a solo. Stars, gas, dark matter, and the black hole all contribute to the potential. Astronomers often define a sphere of influence where the black hole's gravity dominates typical stellar motions. Outside that region, the galaxy's collective mass becomes the main conductor. Energy output adds a final twist. The brightest quasars are not bright because the hole shines. They are bright because infalling matter converts gravitational energy into heat and light. A rapidly feeding black hole can outshine its entire host galaxy, but luminosity depends on fuel supply, viewing angle, and dust, not only on mass. The most massive hole might be quiet, and the loudest might not be the largest. There is also a natural ceiling set by radiation pressure. As a quasar brightens, its light pushes back on infalling gas. The Eddington limit marks a balance point where outward radiation force can match inward gravity for ionized material. Some systems may exceed that limit briefly, but the pushback shapes how fast giants can grow. To keep our scale straight, we need a ladder of black hole classes. Stellar mass black holes form from collapsing massive stars and typically weigh a few to tens of suns. Intermediate mass black holes, if confirmed in large numbers, span hundreds to hundreds of thousands of solar masses. Supermassive black holes sit in galactic centers, from millions to tens of billions of solar masses. Each rung raises new questions about formation, growth, and measurement. Stellar mass black holes are the end states of short, brilliant lives. A massive star exhausts its nuclear fuel, its core collapses, and a supernova may or may not tear the outer layers away. In some cases, the collapse is direct. Matter falls inward so quickly that little light escapes. The remnant is compact, dark, and detectable, mainly through its gravitational influence. Intermediate mass black holes sit in a more uncertain middle ground. They are hinted at in dense star clusters and in some ultraluminous X-ray sources, where brightness suggests a heavier engine. Yet alternative explanations exist, including unusually efficient accretion onto smaller holes. The category matters because it could reveal a stepping stone towards supermassive growth. Supermassive black holes, by contrast, are not rare curiosities. Evidence suggests that most large galaxies host one at the centre, including our own Milky Way. Their masses correlate with properties of the galactic bulge, implying a long coevolution. The black hole is small compared to the galaxy's size, yet it can regulate gas through feedback during active phases. The extremes live at the top of that ladder. Candidates for the most massive known black holes include TON 618, a quasar whose estimated mass reaches tens of billions of suns. Another contender is the central black hole in Holmberg 15A, inferred from galaxy core dynamics and unusually large mass estimates. Some of the Phoenix Cluster's quasar and brightest cluster galaxy systems have also produced enormous claims. At the edge of the chart, every method strains and every assumption matters. With TON 618, the drama is partly about distance and time. We see it as it was when the universe was much younger, meaning its black hole had less time to grow. That makes the mass estimate feel like a challenge thrown at our models. How did something so heavy assemble so early, and what conditions fed it so efficiently? Those uncertainties are not a footnote, they are part of the story. Measuring a black hole's mass is never direct. It is an inference from motion, light, or lensing filtered through models. At high redshift, we rely on bright active nuclei, and brightness can bias samples toward fast accretion and favourable angles. In crowded cluster cores, stellar motions can be hard to disentangle from dark matter and galaxy mergers. The biggest object may shift as methods improve. Even the language of mass hides assumptions. For many quasars, Masses come from broad emission lines produced by fast-moving gas near the nucleus. The line width suggests velocity, and brightness suggests distance from the centre. Put together, they yield an estimate, but the geometry of the gas and our viewing angle can tilt the result. Our tools are varied, and each comes with its own blind spots. Spectroscopy measures how gas moves, broadening lines through high velocities near the centre. Reverberation mapping times the echo between a flickering accretion disk and surrounding gas clouds, turning light delays into size estimates. Stellar and gas dynamics track orbital speeds, converting gravity into mass. Gravitational lensing reads the bending of background light, sometimes revealing mass where no light exists. The Event Horizon Telescope pushes to horizon-scale imaging, resolving the shadow and ring of nearby supermassive black holes. Reverberation mapping in particular turns time into a ruler. When the central disk brightens, surrounding gas clouds respond after a delay, as if answering a call. That lag reveals the size of the region, and combined with velocity information, it constrains the central mass. It is elegant, but it depends on how orderly those clouds really are. Even the HD has limits that shape the hunt. It can image only the closest and largest apparent horizons, not the most massive in the universe. Distance shrinks angular size, and dust and scattering blur the view. For the farthest giants, we will not see a shadow soon. We will weigh them by their influence on matter and light. The EHT's achievement is also a reminder of scale. It links radio dishes across Earth into a virtual planet-sized telescope, using interferometry and atomic clocks to synchronize the data. The resulting image is not a snapshot in the everyday sense, but a reconstruction from sparse measurements. It is still a direct test of strong gravity, and it anchors the concept of a horizon in observation. This is where the tension sharpens. The biggest black hole may not be a single trophy object waiting to be named. It may be a moving target defined by cosmic time, because black holes grow through mergers and accretion. It may be shaped by measurement bias, because we find what our instruments favour. It may depend on definitions, because mass, radius, influence and power do not always agree. There is also a quieter possibility worth holding in mind. Some of the most massive black holes could be dormant, surrounded by little gas, emitting almost nothing. If they do not announce themselves as quasars, they are harder to find and easier to underestimate. The universe may keep its largest examples in the dark, hidden in plain gravitational bookkeeping, yet the quest is still meaningful because extremes test the rules. If a black hole truly reaches tens of billions of solar masses, it challenges models of early growth. It forces us to ask how quickly matter can fall in without blowing itself away. It makes us confront how galaxies and black holes co-evolve. The biggest objects are not just records, they are constraints on the universe's history. Underneath every measurement is the same geometric idea. Gravity is not a force pulling through space in Einstein's picture. Gravity is the shape of spacetime telling matter how to move, and matter telling spacetime how to curve. A black hole is where that curvature closes causal doors. The horizon is the line where outward futures disappear. Time dilation is the human face of that geometry. Clocks deeper in a gravitational well tick differently relative to distant clocks. Near a horizon, the difference becomes extreme in the coordinates of far observers. Signals redshift. Processes appear to slow, and the boundary seems to freeze what crosses it. Locally, the falling traveller notices nothing special at the edge, yet the outside universe becomes unreachable. For the distant observer, the last photons from the infalling object stretch to longer wavelengths. The light dims and reddens until it blends into the background. The object seems to hover, never quite finishing its fall. But for the traveller, the crossing happens in finite time, an ordinary moment, followed by an extraordinary loss of options. That is the deeper replacement for the vacuum myth. Black holes are not defined by hunger, but by a rule about information. They are places where the universe draws a one-way boundary and keeps its secrets. They are both inevitable in the equations and inaccessible in practice. They turn the cosmos into a puzzle with a locked door. Now we can state the central question clearly. What is the biggest black hole we can meaningfully talk about, given our definitions and our measurements? What does its existence reveal about gravity, time, and the limits of observation? The answer will not be a single number alone, but a map of how we know what we know. To find the biggest, we have to understand the rules that make big possible. We have to see how gravity becomes a trap for light, and how that trap becomes a machine for time dilation. From here, we move from myth to mechanism, and from mechanism to the candidates at the edge of the known universe. We left the vacuum myth behind, but the boundary still feels unreal, as if the universe is hiding a seam. The event horizon is not a wall in space, and it is not a glowing rim. It is a rule about which futures remain possible, an accounting of cause and effect. On screen, it is best drawn as a boundary in a diagram, because it is a boundary in time. General relativity replaces gravitational pulling with geometric guidance, and that swap is more radical than it first sounds. Mass and energy tell spacetime how to curve, including pressure and momentum as well as rest mass. Even light contributes, because energy itself gravitates, although its effect is usually subtle. Curved spacetime tells matter and light how to move, because free motion follows the straightest available routes. That statement sounds abstract until you translate it into paths you can picture on a screen. In flat spacetime, the straightest possible path is obvious, like a laser line across a dark room. In curved spacetime, the straightest path bends, because the geometry itself bends beneath it. The technical word is geodesic, but the plain meaning is simple. You move straight, and the universe supplies the curve. If we animate it, we do not show a force tugging the object. We show the grid itself changing shape. Einstein's insight is not that gravity is strong near black holes, although it certainly can be. The deeper claim is that gravity is what we call motion through curved spacetime, measured by how clocks and rulers behave. That is why the field equations talk about stress and energy, not just mass, and why down is a geometric statement. A black hole is where curvature reshapes causality, so thoroughly that outward stops being a future you can reach. If you want intuition, start with escape velocity in Newton's language, because it builds a bridge to the relativistic idea. Escape velocity is the speed needed to climb out without falling back, assuming you do not keep firing engines. Increase the mass or shrink the radius, and the required speed rises because the gravitational potential deepens. It is a clean calculation, and it gives our minds a handle, even though the full story is relativistic. Now push that idea until it breaks, and notice exactly where it breaks. Imagine a compact object so dense that escape velocity reaches the speed of light, c, which is also the maximum speed for information. If light cannot escape, then no slower signal can escape either. Not radio, not particles, not even a shouted warning. The logic is brutal because it is not about engines or strength. It is about the structure of causality. This is the conceptual doorway to the Schwarzschild radius, and it is surprisingly clean. It is the radius where the escape velocity equals c, which in Newtonian terms would be the point of no return. In relativity, that radius becomes the event horizon, a boundary defined by light itself. If we write it out quietly, the radius is proportional to mass, with constants that set the units. It scales linearly with mass, so doubling mass doubles the horizon size, and that simple proportionality will matter again and again. The scaling matters for our central question about the biggest black hole, because bigger does not mean sharper. Bigger mass means a bigger horizon, not a tighter edge, and not a stronger surface gravity in the everyday sense. The geometry expands outward, setting a larger one-way boundary that can swallow solar systems whole. If you could float near it, the horizon would not look like a cliff. It would look like empty space that has lost an exit. Carl Schwarzschild found the simplest black hole solution in 1916, while serving on the Eastern Front during World War I. It describes a non-rotating, uncharged mass, and it was derived astonishingly soon after Einstein published general relativity. The solution is an idealization, but it gives the cleanest map of horizons and time. It also shows how a mathematical expression can predict a physical boundary, even before anyone imagined real black holes in the sky. In that era, the idea sounded like a curiosity, because the astronomical evidence had not arrived yet. In the Schwarzschild picture, the horizon is not a material surface, so there is nothing to scrape against. Nothing special is located there in the local sense, meaning a small falling laboratory detects no sudden spike. The horizon is where outward-directed light rays stop having an outward future, even though they still move at sea locally. That last clause matters, because it prevents the horizon from being a place where light slows down. One way to say it is purely geometric, which is exactly the point of the chapter. The horizon is a null surface, traced by light that just fails to escape, always balancing on the edge of possibility. It is a boundary in space-time, not a shell in space, and that distinction is why the horizon can be invisible. If we visualize it, we can show light rays trying to climb out, then hovering, then sliding inward as the geometry tilts. Gravity becomes geometry most vividly when you ask what happens to time, because time is the ruler we trust most. In relativity, time is not universal, even if it feels universal in daily life. The rate of a clock depends on motion and on gravitational potential, which is another way of saying it depends on the shape of space-time around it. The tick is not a mechanical beat, but an interval between events along a path. Near a deep gravitational well, clocks tick more slowly relative to faraway clocks, and that is not metaphorical. This is gravitational time dilation, and it has been measured near Earth with atomic clocks and satellites. GPS systems must correct for it, because otherwise their timing would drift and location errors would grow. It is not a mechanical slowing of gears, but a difference in space-time intervals, the fundamental ticks between events. Light climbing out of gravity also changes, and the change is not because the photon gets tired. As photons escape, they lose energy relative to distant observers, because energy is defined with respect to time. Their wavelength stretches, and their frequency drops, producing gravitational redshift that can shift visible light into infrared, then into radio, then beyond detectability. In a visualization, a bright blue flare near the hole can fade through red, then into darkness, without any dust or smoke. Time dilation and redshift are two faces of the same structure, like two shadows cast by one object. Both reflect how space-time is warped near compact mass, and both become extreme as you approach a horizon. If you could hover closer and closer, your clock would disagree more and more with the universe far away. The light you send outward would arrive weaker, redder, and later as if the message is being diluted by geometry. The closer you hover, the more fuel you would need, because hovering is not free fall. This is where the story becomes observer-dependent in a precise way, not in a hand-waving way. Different observers slice space-time into different notions of time, and the slicing is built into the coordinates they use. The physics is consistent, but the narratives differ, because when is not the same question everywhere. In relativity, the bookkeeping of time is part of the measurement, not a background assumption. Consider an astronaut falling freely toward a Schwarzschild black hole, with engines off and instruments running. In their own proper time, the horizon is reached in a finite interval, and the equations agree on that. The crossing is not marked by a collision or a shock, and there is no sign that says you are now inside. Locally, the astronaut is just weightless, watching stars distort across the sky. The sky would appear warped into a bright ring, because light is being lensed around the hole. Now consider a distant observer watching the same fall, perhaps from a safe orbit far away. Signals sent up would arrive increasingly delayed and increasingly redshifted, because each successive pulse climbs out from deeper gravitational time dilation. The infala appears to slow, dim, and fade near the horizon, like a candle being lowered behind dark glass. The distant observer can keep receiving photons, but each one carries less usable information. Eventually, the pulses blend into a faint, stretched whisper. The distant observer never receives a final message that says, "I crossed," because the last photons are stretched toward invisibility. The horizon behaves like a one-way boundary for information, not a visible line, and that is why the idea feels so eerie. You can watch someone approach forever in your time, even though they do not experience an infinite fall. The last moments become a kind of asymptote, always nearer, never announced. Both descriptions are true within their frames, and relativity demands we respect both. Proper time for the infala is finite to the horizon, because that time is measured along their path. Coordinate time for the distant observer can diverge, because their time coordinate is tied to faraway clocks. The disagreement is not about facts, but about how facts are labelled in time. It is a reminder that time is part of the geometry we are trying to describe. This difference is not a trick, and it is not a paradox, even if it sounds like one. It is a reminder that simultaneity is not absolute, and it never was, even in empty space. Near a horizon, the question of what is happening now becomes frame-dependent, and now can split into incompatible slices. Which now do we mean? The one on the ship, or the one anchored to distant stars? The biggest black holes sharpen this question rather than soften it, because their scale makes the effects feel architectural. Their horizons are enormous, and their gravitational potentials are deep, yet their edge can be surprisingly gentle. They make time dilation a macroscopic feature, not a microscopic correction, and they turn abstract diagrams into something you could, in principle, fly past. A horizon the size of an orbit is no longer a point on paper. It is a region you can traverse. We can formalize this without drowning in equations, but we should still name what is being compared. The deeper you sit in the gravitational well, the more your time differs from faraway time, and the difference is encoded in the metric. The closer you get to the horizon, the more extreme the mismatch becomes, because the geometry is approaching a causal tipping point. In the Schwarzschild case, the familiar coordinates themselves become strained at the boundary, which is why other coordinate choices are often used. The mismatch is not only about clocks on spaceships, which can feel like a thought experiment. It is also about the light we use to learn, because astronomy is mostly the art of reading photons. If light is redshifted and delayed, then observation itself becomes biased near the boundary. A flare near the horizon can be stretched into a slow fade, and a fast orbit can look slower than it truly is. Even the apparent brightness can be altered by lensing, as photons are focused and defocused by curvature. This is why horizons are effectively invisible, even when the region around them is violently bright. They do not emit a surface glow, and they do not reflect light, because there is no surface to reflect from. We infer them from what light and matter do nearby, and from what they fail to do. The horizon is diagnosed by missing futures, not by a visible edge. In images, the darkness is not paint. It is the absence of escaping paths. The Schwarzschild solution is the starting point, not the end point, and nature rarely grants us perfect simplicity. Real astrophysical black holes are almost never perfectly non-rotating, because the universe is full of spinning gas and orbiting debris. They are born from collapsing, spinning stars, and they grow by accreting orbiting matter that brings in angular momentum. Even a small asymmetry in infalling material can spin a hole up over time. The result is that rotation is not an exception, it is the default. Rotation introduces angular momentum, and angular momentum changes spacetime in a way that has no Newtonian analogue. The relevant solution is the Kerr black hole, found by Roy Kerr in 1963, and it reshaped the field overnight. Kerr geometry is still a vacuum solution, meaning it describes spacetime outside the mass, but it is not spherically symmetric. The symmetry is axial, like a spinning top, and that difference reorganizes the near-horizon world. It also means there are preferred directions, and the universe stops being the same in every orientation. Spin is not a surface spinning like a solid ball, because a black hole has no material surface. It is the conserved angular momentum of the black hole, inferred from the geometry at large distances. In practice, it reflects the history of accretion and mergers that built the object, like a cosmic ledger of past meals. When galaxies collide and their central holes merge, the remnant can inherit a complex spin, tilted and amplified. Over cosmic time, that spin can align with a disk, or it can remain misaligned and restless. A Kerr black hole has a horizon, but the surrounding structure changes, and the change is not cosmetic. Rotation drags spacetime around with it, as if the fabric has been grabbed and twisted. The geometry becomes sheared, and the shear has measurable consequences for orbits, light paths, and the timing of signals. Even the notion of standing still becomes slippery near the spin. The closer you get, the more still becomes a direction you cannot choose. Frame dragging is the name for that twist, and it is one of relativity's most counterintuitive predictions. In Kerr spacetime, inertial frames are pulled around the rotating mass, so gyroscopes precess and orbital planes can shift. Near the hole, even the direction of what counts as non-rotating is altered, because spacetime itself is rotating. Far away the effect fades, but close in it can dominate the choreography. It turns the region into a kind of gravitational whirlpool, not by force, but by geometry. The most dramatic new region is the ergosphere, which lies outside the event horizon like a distorted shell. In the ergosphere, spacetime is dragged so strongly that no observer can remain stationary relative to distant stars. You can still escape, but you cannot stand still, because still would require moving faster than light against the flow. Visually, it is as if the universe becomes a river, and the current accelerates toward the horizon. The surface of that river is not water, but the shifting of what directions remain possible. The ergosphere matters because it opens a door to energy extraction, which sounds like science fiction until you follow the accounting. In the Penrose process, a particle enters the ergosphere and splits, or interacts, in a way that sends one fragment onto a trajectory with negative energy relative to infinity. That fragment falls in, reducing the black hole's rotational energy, while the other escapes with extra energy. The black hole is not violated, its spin is spent. The trick is not magic, it is the strange way energy is defined when spacetime itself is being dragged. The details can be technical, but the core idea is simple and surprisingly elegant. Rotation stores extractable energy in the geometry, and the ergosphere is the region where the bookkeeping allows it. The black hole is not only a sink, it can be a reservoir of rotational power, and the universe can, under the right conditions, draw from it. The limit is not moral but geometric, set by how fast the hole can spin without losing its horizon. In the extreme case, the horizon shrinks, and the boundary between possible and impossible becomes even tighter. In astrophysics, the clean Penrose process becomes a broader theme, because real environments are messy. Magnetic fields and plasma around spinning holes can tap rotational energy, threading the ergosphere and the horizon region with field lines. Jets and high-energy emission can be powered by the spin, not only by infell, and the result can be beams that pierce interstellar space. When we see a galaxy with a bright, narrow jet, we are likely watching geometry pay out energy through electromagnetism. The jet is a lighthouse, and the engine is the twist of spacetime itself. Spin also changes the horizon's size and the inner structure of orbits, which matters for what we can observe. For a given mass, a rapidly spinning Kerr hole can have a smaller event horizon radius than a Schwarzschild hole. It can also allow stable orbits closer in, depending on direction, because prograde motion can ride the frame dragging. Retrograde motion, fighting the twist, is pushed outward, and the disk becomes asymmetric in its efficiency. In spectra, that asymmetry can appear as skewed line profiles, where one wing stretches farther than the other. This is why rotation changes everything about the near-horizon environment. Even though the horizon remains a causal boundary, it affects how efficiently accretion converts gravity into radiation, because the innermost stable orbit sets how deep matter can fall while still orbiting. It affects how matter spirals, heats, and launches outflows, because shear and magnetic turbulence feed on differential rotation. It also affects what the shadow looks like, because light paths are bent differently on the approaching and receding sides. The image becomes a portrait of motion as much as mass. Yet even Kerr does not make the horizon a surface you can touch, and that point is worth repeating with care. The horizon remains a causal boundary, defined by light cones tipping inward, not by a crust. Rotation reshapes the cones, and it reshapes what outward means, but it does not remove the one-way rule. The boundary is still drawn by the future, not by matter. In a sense, the horizon is the place where the map of directions loses a page. The deeper we go, the more the word geometry becomes literal, because the diagrams are not metaphors. In relativity, light cones define what can influence what, and they define the set of possible future paths. Near a black hole, the cones tilt so far that outward becomes impossible, and the set of futures collapses inward. You can imagine the cones as searchlights of possibility, gradually swiveling until they point only down. The animation can be simple, and the meaning can still be profound. At the horizon, the outward direction becomes light-like, meaning only light can hover on the boundary in an idealized sense. Inside, every future-directed path points inward, regardless of thrust, because thrust is still constrained by the local speed of light. The boundary is not a place where gravity suddenly spikes, it is a place where options disappear. That is the real drama, not force, but fate. The universe does not grab you, it edits your list of allowed futures. This brings us to the body's most visceral fear about black holes, which is not time dilation but tearing. People imagine being torn apart at the edge, as if the horizon were a blender. The real threat is tidal force, the difference in gravity between your head and your feet, or between the near side and far side of any object. Tides are what the moon does to Earth's oceans, scaled up to lethal extremes. They are also what stretch comet tails and sculpt rings, because gradients do work. Tidal forces scale with the gradient of the gravitational field, not just the field itself, and gradients care about distance. For small black holes, the gradient near the horizon is steep, because the horizon is close to the mass in absolute terms. For supermassive black holes, the horizon is so large that the gradient can be mild at the edge. The same mass that makes the horizon huge also spreads the change in gravity across a larger distance. It is one of the strangest trade-offs in gravity, and it flips our intuition about danger. This creates the paradoxical safety of enormous holes, a calm threshold hiding a catastrophic interior. You can cross the horizon of a supermassive black hole without immediate spaghettification, at least in principle, and your body would not instantly notice. The fatal stretching can occur later, deeper inside, beyond any chance of warning the outside. The universe allows a gentle step into a region where return is impossible. If we show it visually, the crossing is anticlimactic, which is exactly what makes it unsettling. The same linear scaling that makes horizons larger also spreads out the curvature at the edge, and curvature is the deeper measure of gravity and relativity. A stellar mass black hole can be lethal before you reach the horizon, because the tidal gradient can exceed the strength of chemical bonds. A billion solar mass hole can hide its violence behind the boundary, because the horizon is so far out that the local curvature there can be comparatively small. The danger has not vanished, it has been postponed. The interior still tightens, and the geometry still funnels every future inward. This does not make the interior survivable in any meaningful sense, and it does not rescue the traveller from the end. It changes where the danger peaks, shifting the worst tides inward, where the geometry tightens. It also changes what kinds of signals we might detect from matter near the edge, because matter can orbit and radiate close to the horizon without being instantly shredded. The biggest black holes can host luminous disks that skim the boundary, turning space-time into a furnace. In those disks, friction is not rubbing surfaces, but turbulence and magnetic stresses converting orbital energy into heat. Now the narrative must confront the word singularity, because it sits at the centre of the classical solutions like a final punctuation mark. In classical general relativity, the simplest solutions contain a region where curvature diverges, meaning the mathematical description predicts infinite tidal forces. In Schwarzschild, it appears as a central point hidden behind the horizon. In Kerr, it becomes a ring-like structure, and the interior includes additional horizons in the idealized mathematics. These are not just oddities, because they signal where the equations are being asked to do too much. But singularity is not a photographed object, and it is not a destination we can confirm with instruments. It is a sign that the theory is being pushed beyond its domain, like a map that ends at the edge of the paper. It marks geodesic incompleteness, where the classical description stops giving answers about what happens next. The equations are telling us, with unusual honesty, that something is missing. The closer we get to that missing physics, the less our familiar words deserve their confidence. Many physicists expect quantum gravity to modify the interior, because quantum theory has a history of curing infinities by changing the rules. We do not yet have a tested theory that replaces the singularity with something fully consistent, and competing ideas remain speculative. The singularity is a boundary of knowledge, not a confirmed thing, and that distinction matters for how we speak about it. When we say infinite, we may be hearing the theory confess its limits. The honest question is not what the singularity looks like, but what replaces the concept when the rules change. Cosmic censorship is the related open question, and it hovers over black hole physics like a quiet warning. The conjecture suggests that singularities are always hidden behind horizons, so nature censors naked singularities from distant observers. It is not proven, and it shapes what we think is physically allowed in gravitational collapse. If the censor holds, the universe protects predictability by hiding its most extreme failures. If it fails, the universe may allow exposed regions where the usual idea of cause and effect cannot be cleanly extended. If cosmic censorship fails, the universe could expose regions where predictability breaks down, and the rules of cause and effect become ambiguous. If it holds, horizons protect the outside from the deepest inconsistencies, sealing the unknown behind a causal curtain. Either way, the biggest black holes become laboratories for the limits of the theory, because their environments can be measured with extraordinary precision. They're not just monsters, they are tests. And the tests are not performed in a lab but in the sky, using light and time as instruments. The mystery deepens when you return to time, because time is the thread that stitches observations into stories. If time slows near a horizon relative to the far universe, then the meaning of now becomes slippery, even for careful observers. Different observers disagree on what events are simultaneous, and the disagreement grows near extreme gravity. In a sense, the horizon is where the universe forces us to admit that now is not a universal broadcast. It is a local agreement negotiated by the geometry around you. For a distant observer, processes near the horizon appear slowed and reddened, and the last stages of infale smear into a long twilight. For the infaler, local physics remains normal until tidal forces become strong, because the equivalence principle still holds in a small enough region. The horizon is ordinary locally, yet extraordinary globally, and that duality is the chapter's central tension. How can a place be both unremarkable and absolute? The answer is that the drama is not in the local sensation, but in the global connectivity of spacetime. This split viewpoint is not merely philosophical, and it is not only a classroom puzzle. It affects how we interpret observations of accretion flows and flares, where timing and brightness are the clues we have. It affects how we model the timing of signals and how we infer mass and spin from light curves and spectral lines. When we see a hotspot orbiting near the inner disk, we're watching geometry modulate time. The flicker is not just plasma physics, it is relativity writing on the light. It also frames the central question of the documentary, because biggest is not just a number. The biggest black hole is not only a mass number on a chart, and it is not only a radius you can compute. It is a place where our everyday timekeeping loses its authority, and where the sky itself becomes a lens. The champion, if we find it, will be defined as much by spacetime behavior as by kilograms. In the end, biggest is also most reshaping, because mass is geometry's sculptor. If horizons are invisible, then evidence must be indirect, and indirect evidence demands careful skepticism. We look for fast orbital motion of stars and gas, because velocity reveals enclosed mass without needing to see it. We look for the heating and redshift of matter spiraling inward, because gravity turns ordered motion into thermal chaos. We look for lensing patterns, shadows, and the timing signatures of extreme gravity, because light paths are bent by curvature. Each clue is partial, and the art is in making them agree. In the best cases, we can watch stars trace tight ellipses around an unseen center, their speeds rising as they swing through pericenter. In other cases, we read the disk's spectrum, seeing broadened iron lines shaped by Doppler shifts and gravitational redshift together. We also compare images to simulations, where the dark shadow is not the horizon itself, but the silhouette of captured light. Each method is a different angle on the same rule. Some paths do not come back. The more methods converge, the more the invisible boundary becomes a measurable fact. We also listen for gravitational waves, because they carry information that light cannot. Merging black holes shakes spacetime itself, carrying away energy and angular momentum as ripples that pass through Earth. The waveforms encode masses and spins, and they test whether the final object matches Kerr's predictions. In those signals, we hear geometry ring like a bell, and the tone tells us what the bell is made of. After the merger, the ring down is a fading chord, and its frequencies are the black hole's fingerprint. These observational stakes are not separate from the theory, and that interdependence is the modern scientific method in action. The theory tells us what signatures to expect, and the signatures tell us whether the theory's geometry is right. Every measurement is a negotiation between model and data, and every model is constrained by what the sky refuses to do. When observations agree, confidence grows, but the horizon remains a boundary we infer rather than touch. We're always reconstructing the unseen from the behavior of what escapes. The biggest black holes push that negotiation to its limit, because scale cuts both ways. Their horizons are large, but their distances are vast, so angular sizes can be tiny even when the object is enormous. Their accretion can be bright, but it can also be hidden by dust, orientation, or starvation, leaving a giant that is quiet. Some of the largest may be almost invisible, defined by what they control rather than what they emit. A galaxy can orbit an absence and still be shaped by it. So Chapter 2 is not about naming a champion, and it is not about crowning a single object in a cosmic ranking. It is about learning the rules that make champions possible, and the rules are geometric. It is about understanding how mass, radius, time, and spin are tied together by geometry, and how that geometry dictates what can be seen. The horizon is the chapter's main character, even when it refuses to appear on camera. We can only film its consequences, and that is the point. That brings us to the documentary's quest. If gravity can become geometry, then growth becomes a story of reshaping space-time itself, one merger and one accretion episode at a time. The next step is to ask how black holes are made, how they feed, and how they become giants. We will follow matter as it falls, heats, radiates, and sometimes escapes in jets, always negotiating with the curves of space-time. To find the biggest, we have to understand the rules that make big possible. From here we leave pure geometry and follow the cosmic supply chain, because mass does not appear by magic. We track collapse, accretion, mergers, and the long climb toward galactic anchors. Along the way, we'll keep asking the same quiet question. When space-time itself is the stage, what does it mean to grow? To find the biggest black hole, we have to understand how black holes are made, because mass is not just a number. The horizon is a rule of geometry, but mass is a history of collapse, layered, contingent, and shaped by what escaped. Black holes begin as endings, and the camera should linger on a star that looks calm only from far away. In its core, nuclear fusion is a negotiated truce between pressure and gravity, and it lasts only while fuel remains. A massive star burns through hydrogen, then helium, then heavier elements in successive shells, like an onion lit from within. Each stage runs faster than the last, because the star must work harder to resist its own weight. Eventually it builds an iron core, and iron is where fusion stops paying the bills. Fusing iron does not release energy, so the core becomes a dead weight at the centre of a living furnace. With no new energy source to replenish pressure, gravity takes the lead, and the core collapses in milliseconds. The outer layers respond in violence or in silence, depending on how the collapse couples to the star's envelope. In a core collapse supernova, the infalling core compresses to nuclear densities, and matter becomes as stiff as an atomic nucleus. The collapse halts abruptly, and the inner core rebounds, launching a shock wave into the still infalling material. For a moment, the shock looks like a clean solution, but it loses energy by breaking apart heavy nuclei and by radiating neutrinos. The shock can stall, hanging in the star like a wave frozen in mid-break. Neutrinos then become more than ghostly byproducts, and this is one of the strangest turns in stellar death. In the first seconds after collapse, the newborn proto-neutron star floods space with neutrinos, carrying away most of the gravitational binding energy. A small fraction of that neutrino energy can be reabsorbed behind the stalled shock, reheating the region and helping the shock revive. If the revival succeeds, the shock unbinds the envelope and the star tears itself open into space. If the explosion is weak, much of the envelope does not truly escape, and the visual should show debris that hesitates. Material can be launched outward, slow, and then fall back through the shock-heated wreckage like rain returning to a crater. That fallback feeds the remnant and raises its final mass, sometimes by several solar masses. The difference between a neutron star and a black hole can be decided by matter that almost got away. Fallback is a second collapse after the first collapse, and it is governed by energy bookkeeping. The outward-moving gas loses kinetic energy to expansion, radiation, and collisions, and gravity quietly keeps the ledger. When the gas can no longer climb, it turns around and returns inward, often in a chaotic, asymmetric flow. That returning mass can push a neutron star over its maximum stable mass, forcing it to collapse into a black hole, or it can grow a black hole that already formed, deepening the gravitational well that pulls even more material back. Some stars skip the fireworks, and the documentary should let the silence feel unsettling. In direct collapse, the core forms a black hole quickly, and the envelope follows with little luminous display. There may be a faint transient, a whisper of light from a brief shock or a weak outflow, but nothing like a classic supernova. The event can be optically faint, yet it can seed a compact object with a larger starting mass, an advantage that echoes later in cosmic time. Typical stellar mass black holes land in the range of a few tens of solar masses, and that range is not arbitrary. It reflects how much of the star's mass ends up in the final core and how much is lost before death. Rotation matters because it changes mixing, core growth, and the star's ability to launch winds. Binary companions matter too because mass transfer can strip envelopes and rewrite the ending, even when the beginning looked ordinary. In the most extreme cases, remnants can reach higher, but pair instability physics can carve a gap. At very high core temperatures, energetic photons can convert into electron-positron pairs, reducing radiation pressure and triggering runaway contraction. That contraction ignites explosive oxygen burning, and the star can either pulse violently or be completely disrupted. In full pair instability supernova, no black hole is left behind, and a swath of initial masses is erased from the remnant census. Metallicity quietly controls the outcome, and it does so through the physics of starlight pushing on atoms. In high metallicity stars, heavy elements provide many spectral lines that absorb radiation, driving strong line-driven winds. Over millions of years, those winds peel away mass, leaving lighter cores at death and therefore lighter remnants. In low metallicity stars, winds are weaker, the star keeps more of itself, and the final collapse can deliver heavier cores that more readily form massive stellar black holes. This is the first rung on the ladder, and it is a rung we can test with nearby remnants and gravitational wave detections. Stellar remnants show that gravity can lock away a star, but they do not explain galactic-scale giants. The central question returns with new force, because the scale jump is enormous. How does a black hole climb from tens of suns to billions without running out of time or fuel? Between stellar and supermassive lies a suspected missing link, and the visuals should shift to a ladder graphic that feels incomplete. Intermediate mass black holes would span roughly hundreds to hundreds of thousands of solar masses, bridging a gulf in formation physics. They matter because they could be stepping stones, letting growth proceed in fewer leaps and fewer e-foldings. If they exist in large numbers, the early universe has a more forgiving path to its first giants. The evidence is frustratingly thin, partly because intermediate mass black holes would be small targets in crowded places. In globular clusters, a central dark mass could be an intermediate black hole, or it could be a dense swarm of stellar remnants. White dwarfs, neutron stars, and stellar mass black holes can sink toward the center through mass segregation, building a compact, invisible core. The dynamical signature is subtle because the sphere of influence is tiny, and the stars that trace it are packed together. Astronomers look for a rise in stellar velocity dispersion toward a cluster's center, because gravity should stir stars faster near a massive object. They also look for proper motions that curve around an unseen mass, tracing arcs that hint at a central anchor. But mass segregation can mimic a central mass by concentrating heavy remnants, and binary stars can inflate measured velocities. Limited resolution adds another layer of ambiguity, because blended starlight can hide the very stars needed for clean measurements. Even the concept of a center can be slippery in a cluster, and that complicates the story. Globular clusters are not perfectly relaxed spheres, and their cores can wander or oscillate. A black hole, if present, might not sit exactly at the photometric center at every moment. When the signal is small, these details matter, and they can turn a promising claim into a cautious upper limit. Dwarf galaxies offer another hunting ground, and they shift the search from star clusters to miniature galactic nuclei. Their shallow gravitational potentials and small bulges could host intermediate black holes that never grew into supermassive ones. In that sense, dwarfs may preserve earlier evolutionary stages, like fossils embedded in the modern universe. Yet dwarf nuclei are faint, and their accretion can be intermittent, making luminosity a poor guide. Low luminosity is a double trap, and it can mislead even careful observers. A quiet black hole leaves little electromagnetic evidence, and a weakly accreting one can hide behind dust and star formation. Gas clouds lit by young stars can produce emission lines that resemble those from an active nucleus, blurring classification. Even when an active nucleus is present, it can be confused with stellar processes, supernova remnants, or compact X-ray binaries. Still, the search continues because the middle rung changes the whole story, and the stakes are not merely cataloguing. If intermediate black holes are common, hierarchical growth becomes easier to build, and early quasars become less paradoxical. If they are rare, the universe may have used a different shortcut, perhaps relying on heavier seeds or brief periods of exceptional accretion. Either way, the missing link is a test of how nature prefers to assemble mass. Now we step into the centers of galaxies, where the giants rule and the narration should slow down. Supermassive black holes sit in galactic nuclei, with masses from millions to tens of billions of suns. They are small in size compared to their galaxies, yet they can dominate the inner gravitational choreography. Stars, gas clouds, and even whole star clusters move as if guided by an invisible conductor. Two nearby anchors keep the story grounded, and they also show how measurement becomes possible. Sagittarius A sits at the Milky Way's centre, about 4 million solar masses, measured by stellar orbits tracked over decades. The visuals can show infrared points of light tracing tight ellipses, speeding up near pericenter like comets. Those orbits are not artistic impressions, but data, positions and velocities that lock the mass into a narrow range. M87T sits in a giant elliptical galaxy, with a mass of billions of solar masses, and it occupies a different observational regime. Its surrounding plasma powers a relativistic jet that extends thousands of light years, a lighthouse beam carved into intergalactic space. The Event Horizon Telescope imaged the shadow-scale structure, revealing a ring of emission shaped by strong gravity. Here the measurement is not from stellar orbits, but from horizon-scale light bending and from gas dynamics in the nucleus. These anchors are not the biggest candidates, but they are the clearest laboratories, and laboratories teach us what to trust. They show that supermassive black holes are real, common, and measurable, with multiple methods that cross-check one another. They also show that a black hole can be quiet or violently active, depending on fuel supply and how that fuel loses angular momentum. In one galaxy, the nucleus is a faint radio source. In another, it is the brightest object for billions of light years. The deeper mystery appears when we look far back in time, and the visuals should pull outward into a deep-field sky. At high redshift, quasars shine when the universe was less than 1 billion years old, and their light is stretched red by cosmic expansion. Many of those quasars require central black holes around 1 billion solar masses, already assembled while galaxies were still forming their first mature structures. The implication is stark. The universe built monsters early, and it did so repeatedly. That claim is not casual, and it rests on several converging lines of inference. Quasar luminosities imply enormous accretion power, because only gravity can plausibly supply that energy budget for so long. Broad emission lines imply fast gas bound to a deep potential, with velocities of thousands of kilometers per second. Put together, the inference is a supermassive black hole already in place, when cosmic history was still young. The tension is mathematical as much as astronomical, and it can be stated as a growth problem with deadlines. If a seed starts small, growth must proceed through accretion and mergers, but both take time. The early universe does not grant much time, because the first quasars appear within a few 100 million years of the first stars. When the target is 1 billion solar masses, even small inefficiencies become fatal. Accretion is the main engine of growth, and it is also the main speed limit because light fights back. Gas falling inward forms a disk because angular momentum resists direct plunge, and the disk must shed that angular momentum to feed the center. Friction in the everyday sense is not enough, but magnetic turbulence can act like an effective viscosity. In many models, the magneto-rotational instability tangles magnetic fields and transports angular momentum outward, letting mass drift inward. Radiation is not a side effect. It is the bill for falling deeper, and it must be paid in photons. As gas spirals inward, gravitational potential energy becomes heat, and heat becomes light across the electromagnetic spectrum. The inner disk can reach temperatures that radiate in ultraviolet and X-rays, while dust farther out re-radiates in infrared. The brighter the disk becomes, the harder it is for new gas to keep falling, because radiation pressure couples to electrons and to dust. The Eddington limit names the balance point, and it is a simple idea with profound consequences. Gravity pulls ionized gas inward, while radiation pressure pushes electrons outward through Thomson scattering. At the Eddington luminosity, the outward push can match the inward pull for spherical inflow, setting a characteristic maximum steady brightness. Real accretion is not perfectly spherical, yet the Eddington concept remains a powerful benchmark. Brightness translates into a growth rate, and the translation is where the time problem sharpens. If a black hole radiates near the Eddington limit with a typical efficiency, its mass grows exponentially with a fixed e-folding time. That timescale is tens of millions of years, long enough that repeated doublings are required to reach quasar masses. Starting too small makes billion solar mass targets hard to reach early, unless the feeding is unusually persistent. Efficiency is the second constraint, and it is a constraint hidden inside the light we observe. A fraction of the infalling mass energy is converted to radiation, and the rest adds to the black hole. Higher efficiency means more light per unit mass, which means stronger pushback and slower mass gain for the same luminosity. In plain terms, A brilliant engine can be a slow builder, because it wastes more mass as light. Spin links to efficiency, because it sets how deep stable orbits can go before matter plunges. A rapidly spinning black hole allows the inner edge of the disk to sit closer to the horizon, where more gravitational energy is available. That raises radiative efficiency, making the quasar brighter for a given mass inflow, but it also makes growth harder. The universe must therefore balance two competing desires: shine brightly, yet gain mass quickly. So the standard picture has a built-in dilemma, and the narration should let that dilemma hang in the air. To grow fast, you want low efficiency and high inflow, but luminous quasars suggest high radiative output. The universe either found heavy seeds, or it found ways to exceed the standard assumptions without blowing itself apart. The puzzle is not whether black holes can grow, but how they grew so fast so early. One escape route is super Eddington accretion, and it requires conditions that change how radiation behaves. In dense, optically thick flows, photons can be trapped and advected inward with the gas, rather than diffusing outward to push it away. The disk can feed the black hole faster than its light can push back, at least for limited periods. Outflows may still occur, but the net inflow can remain high enough to accelerate growth. Another escape route is hidden growth, and the visuals should show a nucleus wrapped in dust like a cocoon. Dust and gas can obscure the central engine, letting a black hole gain mass while its light is absorbed and reprocessed into infrared. If much early growth is buried, our census of bright quasars may miss the full mass-building phase. The universe could have built giants behind curtains, revealing them only after the dust was cleared. The seed problem becomes the chapter's central puzzle, because the starting point determines how hard the race becomes. What was the first black hole in a young galaxy, and how massive was it at birth? 3 broad scenarios compete, and each carries different predictions about environments, numbers, and timing. The answer is not only about black holes, but about the first structures that could feed them. The first seeds could be remnants of population 3 stars, and this idea reaches back to the universe's earliest chemistry. The earliest stars formed from pristine hydrogen and helium, with almost no metals to help gas cool and fragment. Many models suggest these stars were massive and short-lived, living fast because their cores burned hot. Their deaths could leave black holes of tens to perhaps hundreds of solar masses, depending on mass loss and pair instability outcomes. Population 3 remnants are attractive because they are inevitable, and inevitability is a powerful argument in cosmology. If the first stars existed, some fraction should have collapsed into black holes, sprinkling the early universe with seeds, but they start small, and small starts make the time problem severe. To reach 1 billion solar masses quickly, they need near-continuous near-Eddington feeding, or repeated super-Eddington episodes that do not self-destruct. A second channel uses dense star clusters, and it relies on gravity's tendency to concentrate mass. In a compact young cluster, repeated stellar collisions can build a very massive star, especially if the cluster is dense enough that encounters are frequent. That swollen star can then collapse into a larger black hole, providing a heavier seed than a single ordinary supernova. Alternatively, runaway mergers of stellar mass black holes can assemble a heavier seed over time, although the pathway is messy. Cluster channels can produce seeds in the range of thousands of solar masses in optimistic cases, and that would ease the growth requirements. But they require special conditions, including high densities and rapid mass segregation, that brings the heaviest objects to the center. They also risk ejecting black holes through gravitational recoil during mergers, losing the seed at the very moment it forms. The cluster must be both crowded and lucky, a combination the universe may not always provide. The third channel is the most dramatic shortcut, and it changes the scale of the first step. Direct collapse black holes could form when a pristine gas cloud collapses without fragmenting into normal stars. If cooling is suppressed, the cloud can funnel mass into a single object, forming a supermassive star or a quasi-star phase that quickly collapses. The result could be a seed of 10,000 to 1 million solar masses, a head start that reshapes the timeline. Direct collapse demands a narrow environment, and the narration should emphasize how specific the conditions are. The gas must remain metal poor, because metals enhance cooling and encourage fragmentation into many small stars. It must also avoid forming many stars early, because stellar feedback would blow out gas and steal mass from the central inflow. A strong ultraviolet background can dissociate molecular hydrogen, reducing cooling and helping the collapse stay monolithic. If direct collapse happens, the early universe puzzle softens, because the arithmetic becomes less punishing. A heavier seed needs fewer E-foldings to reach quasar masses, even under Eddington limited growth. But the rarity of the required conditions becomes the new question, and the observations must decide. Are these seeds rare exceptions, or were they common enough to explain the earliest quasars? Accretion alone is not the only path upward, because the universe builds structure by assembly. Mergers build mass in discrete jumps, and galaxies themselves grow hierarchically through repeated collisions and accretions. When galaxies merge, their central black holes are carried inward by dynamical friction, as the surrounding stars and dark matter absorb orbital energy. The process is slow on human timescales, but relentless on cosmic ones. When two galaxies merge, their black holes sink toward the new center, and the visual should show two bright nuclei spiraling together. They form a bound binary, then harden by interacting with surrounding stars and gas, like a slingshot exchanging energy. Each interaction extracts orbital energy, shrinking the separation and preparing the system for gravitational wave-driven in spiral. The binary's environment becomes part of the engine, because without it the orbit cannot tighten. This is where a famous bottleneck appears, and it has shaped decades of theoretical work. At separations of about a parsec, the binary can stall if it runs out of stars on intersecting orbits that can carry energy away. The final parsec problem asks how binaries keep losing energy when the easy supply of scatterers is depleted. It is a question about geometry and probability as much as gravity, because it depends on how orbits refill the loss cone. Nature has several possible answers, and each answer depends on the messy reality of galaxies. Traxial galaxy potentials can keep refilling the loss cone with new stars, because non-spherical shapes allow more wandering orbits. Gas disks can torque the binary, extracting angular momentum and driving it inward through gravitational interactions and shocks. Repeated minor mergers can perturb the nucleus and keep the hardening process active, preventing the binary from settling into isolation. If the binary reaches milliparsec scales, gravitational waves take over, and the story becomes one of space-time itself. The inspiral accelerates, the system radiates energy in ripples that propagate outward at light speed, and the black holes merge. The remnant can receive a recoil kick from asymmetric radiation, a momentum imbalance that can displace it from the galactic center. In small galaxies, that kick can even eject the remnant, turning a growth event into a loss. Mergers also reshape spin, and spin is not a trivial detail because it affects both light and growth. Randomly oriented mergers can produce moderate spins because angular momentum vectors partially cancel in a cosmic shuffle. Prolonged disk accretion can align and spin up the whole, because the disk's angular momentum acts like a steady hand on a wheel. Spin then feeds back into radiative efficiency, and efficiency feeds back into growth speed, closing a loop of cause and consequence. Growth is not only a private story inside the nucleus, and the visuals should widen to show whole galaxies breathing. Black holes and galaxies co-evolve, and the evidence is written in correlations that span many orders of magnitude. The M-sigma relation links black hole mass to the velocity dispersion of the galactic bulge, implying a shared history of regulation. It is as if the galaxy remembers what its black hole became, and the black hole remembers what its galaxy allowed. Feedback is the proposed regulator, and it is a mechanism that turns accretion into influence. When a black hole accretes, it can launch winds and jets that heat, expel, or stir the surrounding gas. That energy can quench star formation, limit further accretion, and set a balance between bulge growth and black hole growth. The same process that builds the black hole can also starve it, creating a self-limiting cycle. Feedback comes in different modes, and the mode depends on how the black hole is fed. Radiative winds can push on dusty gas and drive wide-angle outflows during bright quasar phases, sweeping cavities through the interstellar medium. Jets can deposit energy into hot halos, inflating bubbles visible in X-ray images and preventing cooling flows. In massive ellipticals and galaxy clusters, those jets can act like thermostats, keeping gas from condensing into new stars. This regulation is not gentle, and it is not always efficient because galaxies are turbulent systems with competing timescales. Some galaxies show bursts of star formation alongside active nuclei, suggesting complex timing rather than simple suppression. Gas can flow in along cold filaments, ignite a starburst, and only later trigger a luminous accretion episode. but the broad cosmic averages hint at a coupled cycle, where gas supply feeds both stars and black holes, then feedback throttles both. Observations provide the statistical clues, and the documentary should shift from individual objects to populations. Quasar luminosity functions map how the number of bright accretors changes with redshift, turning surveys into a kind of census. They show a rise toward cosmic noon, then a decline, tracing when the universe most efficiently fed its central engines. Behind those curves is a changing balance of gas supply, merger rates, and feedback strength. Duty cycles translate those counts into lifetimes, and they remind us that activity is episodic. A galaxy may host a supermassive black hole for billions of years, but it shines as a quasar only in episodes that may last millions of years. The fraction of time spent active constrains how much mass can be gained through luminous accretion. It also hints at how often galaxies deliver gas to their centers, and how often feedback interrupts the delivery. The cosmic star formation history offers a parallel curve, and the parallel is too suggestive to ignore. Star formation peaks around redshift 2, then fades, and black hole accretion history broadly tracks it. The match suggests shared fuel and shared regulation, even if the detailed timing differs from galaxy to galaxy. When the universe was rich in cold gas, it built both stars and black holes at its fastest pace. Yet the earliest quasars remain the sharpest thorn, because they sit at the edge of what standard growth allows. Their existence implies that some black holes found abundant fuel, avoided catastrophic feedback too early, and grew rapidly in the first few 100 million years. The universe seems to have built thrones before it built many of the kingdoms, and that inversion is a clue. Did the first galaxies funnel gas inward more efficiently than later ones, or did the first seeds begin far heavier than we expect? This is where the documentary's central question gains a new edge, and it becomes more than a search for a record holder. The biggest black holes are not just large, they are ancient, and their mass is a record of early cosmic conditions. If we can explain their growth, we learn how gravity, gas, and time negotiated the first galaxies. We also learn which assumptions in our models are robust, and which are conveniences that the universe ignores. But explanation requires measurement, and measurement is hardest where the giants are farthest, because distance erodes detail. If much growth is obscured, and if seeds vary by environment, we need ways to weigh the invisible without seeing the horizon. We need mass estimates that survive distance, dust, and bias, and that can be compared across cosmic time. The methods must convert motion, light, and variability into numbers we can trust. That brings us to the next step in the journey. If black holes hide behind one-way boundaries, then the biggest ones hide behind the universe's longest light travel times. The next chapter asks how astronomers measure mass across that gulf, and how confident we can be. To find the biggest, we have to learn how to weigh what cannot be touched. We will follow the methods that turn motion, light, and time delays into mass. Then we will return to the candidates at the edge and ask which giants truly deserve the crown. We have learned how black holes grow, but growth stories collapse without reliable weights, especially when the prize is a record. The central question returns with teeth, because it sounds simple and yet refuses to stay pinned down. What is the biggest black hole we can meaningfully talk about, and what does biggest even mean? A black hole does not come with a scale, and it rarely comes with a clean outline against a clean background. We infer mass from what moves, what shines, and what flickers, then we translate those clues into gravity's hidden bookkeeping. Even the word mass is shorthand for spacetime curvature, because in general relativity, mass, and geometry are inseparable. The first lesson is humility, because mass measurements are model-dependent even when the data look crisp. The second lesson is that uncertainty is not a footnote. It is part of the result and part of the story. The title of biggest is contested because different rulers disagree at the extremes, and because the extremes are where small biases become enormous numbers. In the mind's eye, the problem is visual and immediate. Imagine a galaxy nucleus as a crowded stage, with stars and gas moving in complicated patterns under dim, overlapping spotlights. Somewhere at the center is an unseen weight, silent, compact, and dominant. Yet we never touch it directly. We only watch the choreography and ask what kind of mass could conduct it. Nearby, quiet giants offer the cleanest physics, because their light does not drown everything else in glare. In quiescent galaxies, we can treat the nucleus as a gravitational problem, not a brightness problem with a tiny signal buried inside. The goal is simple in principle. Measure how fast matter moves, then infer the mass required to bind it. That logic is old, and it is comforting because it echoes how we weigh the Sun using planetary orbits. Newton's gravity connects orbital speed and radius to enclosed mass, and the same relationship survives in the weak field limit around supermassive black holes. Close enough to the center, the black hole should dominate, and the motion should approach a Keplerian pattern. Stellar dynamics is the classic approach, and it begins with star velocities near the center where the gravitational pull is steepest. We measure Doppler shifts for line-of-sight speeds, and proper motions when we can resolve them across years of imaging. If stars orbit an unseen point, their speeds rise as radius shrinks, and the enclosed mass reveals itself. The visuals here can be deceptively serene. A telescope image shows a smooth, golden bulge, yet the spectroscopy turns that glow into thousands of tiny stellar fingerprints. Each absorption line is slightly shifted, and those shifts map a velocity field like weather patterns over a continent. The black hole is not seen, but it is written into the gradients. The method is powerful because stars are test particles that do not feel radiation pressure in the way gas does. It is also demanding because the sphere of influence can be tiny on the sky, even for very massive objects. The sphere of influence is where the black hole's gravity dominates over the surrounding bulge, and it sets the resolution requirement. That sphere has a simple scaling that hides a practical nightmare. Its radius grows with black hole mass, but it shrinks with the square of the host's stellar velocity dispersion, and then distance turns it into a minuscule angle. For many galaxies, the region we need is smaller than a pixel unless we use adaptive optics or space-based imaging. If we cannot resolve that region, the galaxy's own mass distribution can mimic the signal we are trying to isolate. A steep stellar density cusp can look like a heavy black hole if the model is wrong, because the stars themselves contribute gravity. Dark remnants and orbital anisotropy can also bias the inferred mass, because not all stars move the same way. Orbital anisotropy is a quiet troublemaker, because it is invisible until you model it. If many stars prefer radial orbits, line-of-sight velocities can look inflated near the center, even without extra mass. If many stars prefer tangential orbits, the opposite happens, and the black hole can be underestimated. The data constrain the possibilities, but they rarely eliminate them. Stellar dynamical modeling is therefore an exercise in assumptions about orbits, symmetry, and the stellar mass-to-light ratio. We fit families of possible stellar trajectories to the observed light and velocity field, often using orbit superposition techniques that explore huge libraries of paths. The result is a probability distribution, not a single number, and the tails matter most for record claims. Those tails are where the drama lives, because biggest is decided by the far end of a distribution. A best-fit mass might be enormous, yet a plausible model family may allow a much smaller value, depending on the adopted dark matter halo. When the claim is tens of billions of solar masses, even a modest shift in assumptions can reorder the leaderboard. Gas dynamics offers another route, and it can be cleaner or messier depending on the system's temperament. Ionized gas emits narrow lines whose Doppler shifts trace rotation and turbulence, and those lines can be mapped across the nucleus with integral field spectroscopy. If the gas forms a disk, its rotation curve can approximate Keplerian motion, and mass follows from speed. When it works, the picture is striking. You see a thin, luminous disk often threaded by dust lanes, with one side blue-shifted and the other red-shifted like a spinning coin. The velocity rises inward, and the curve can reveal a central point mass as clearly as a signature. Yet the disk must be orderly, and nature is rarely that polite. But gas is not collisionless, and it is easily disturbed by forces that stars mostly ignore. Pressure support, shocks, inflows and outflows can inflate velocities beyond pure gravity, and turbulence can broaden lines in ways that mimic rotation. Non-circular motion can masquerade as extra mass, and dust can hide the inner disk where the signal is strongest. AGN feedback can complicate the scene even when the nucleus is not a blazing quasar. Jets can stir the interstellar medium, and radiation can ionize gas into filaments that do not trace circular orbits. Even a modest central engine can drive winds that add asymmetric velocity components. The disk you want becomes a disk you must prove. High angular resolution is the common bottleneck for both stars and gas, and it shapes what is even measurable. The biggest nearby black holes can still subtend tiny angles, Because galaxies are far and the relevant region is compact. Adaptive optics, space telescopes, and interferometry become part of the mass measurement, not just a technical detail. Adaptive optics is a quiet revolution that deserves a moment because it changes the practical limits of dynamical work. By correcting atmospheric turbulence in real time, it sharpens the point spread function and concentrates light into a tighter core. That extra sharpness is not cosmetic. It decides whether the sphere of influence is resolved or blurred away. Masers are the precision tools that sometimes cut through the fog, and their elegance feels almost unfair. In rare galaxies, water molecules in a thin, edge-on disk amplify microwave emission into bright, narrow Mesa lines. Those lines trace specific radii in the disk, like beacons pinned to circular orbits. The visual is almost geometric. Imagine a dark lane of molecular gas circling a hidden center, and then imagine a few bright points along that ring, each one a natural laser at 22 GHz. With very long baseline interferometry, those points become measurable positions on the sky, separated by microarc seconds. The disk turns into a ruler. With masers, we can map a clean Keplerian rotation curve with exquisite accuracy, because the lines are narrow and the orbits are well defined. We measure velocities from Doppler shifts and positions from very long baseline interferometry, then connect speed and radius through gravity. The geometry gives the central mass with minimal astrophysical modelling, because gravity dominates the disk dynamics. Some maser systems also yield geometric distances through proper motions and accelerations, which is a rare gift in extragalactic astronomy. As maser spots drift over time, their angular motion combines with their line-of-sight acceleration to triangulate distance. That distance breaks degeneracies that plague other methods, and it strengthens the mass estimate. It is one of the closest things astronomy has to a direct weighing of a supermassive black hole. The disk is thin, the orbits are close to circular, and the measurement rests on geometry rather than on uncertain stellar populations. When a maser system cooperates, it becomes a benchmark that calibrates other techniques. Masers are rare because the conditions are narrow and orientation dependent, and the universe does not optimize itself for our convenience. The disk must be dense, warm, molecular, and viewed nearly edge-on, so that the gain path aligns with our line of sight. The maser amplification must be high, and many galaxies simply do not cooperate. Precision exists, but it is not widely available, and that scarcity shapes the field's confidence. A handful of maser galaxies anchor the mass scale with extraordinary clarity, while most galaxies must be weighed with methods that carry heavier modelling baggage. The result is a patchwork of certainty, stitched together across distance and circumstance. These local methods anchor our confidence, yet they do not reach the farthest giants that tempt the record books. The biggest candidates often live at cosmological distances where individual stars are unresolvable and even gas disks blur into a single pixel. There, the black hole announces itself through activity, and activity changes the measurement game. Active galactic nuclei are not the hole, but they are the hole's feeding signature, and they are among the brightest phenomena in the universe. Gas spirals inward, heats through friction and magnetic turbulence, and radiates across the spectrum from radio to X-rays. In the brightest cases, a quasar outshines its host galaxy, turning the nucleus into a beacon visible across the observable universe. That beacon carries a paradox. The very brightness that makes quasars easy to find also makes their environment harder to interpret, because glare erases the host and saturates the central region. We are forced to infer mass from the light of the feeding process, not from the quiet motion of orbiting stars. The ruler becomes indirect, and the assumptions multiply. AGN spectra carry a key clue in their broad emission lines, which look like smears where narrow lines should be. In the broadline region, gas moves at thousands of kilometers per second, and Doppler broadening spreads the lines into wide wings. Those velocities suggest deep gravitational binding, but we do not see the orbits directly. The broadline region is a zone of extremes, and it sits at a scale that is tiny by galactic standards. It is larger than the innermost accretion disk, yet far smaller than the host galaxy's bulge, and it is likely structured rather than uniform. Clouds, streams, or a thick disk may coexist, lit from within by the central continuum source. We read its physics from line shapes, asymmetries, and variability. The virial method turns broad lines into mass by assuming the gas is gravitationally bound and roughly virialized. The core idea is simple, and it is the same logic that weighs star clusters. Mass scales like velocity squared times radius divided by the gravitational constant. The hard part is that the radius is not directly imaged. Even the velocity is a proxy because we measure a line width, not a three-dimensional speed. The full width at half maximum and the line dispersion capture different aspects of the profile, and each responds differently to noise and to non-virial components. A line with a strong blue wing might be telling a wind story, not an orbit story. The method can work, but it must be interrogated. Reverberation mapping supplies that missing radius through time, and its logic is almost cinematic. The AGN continuum varies as the inner accretion flow brightens and dims, sometimes over days and sometimes over months. The broad lines respond after a delay, because light must travel to the broadline gas and back to us. That time delay gives a size scale for the broadline region, because distance equals light speed times lag, and light speed is the one constant we can trust. Combine that size with the line width as a velocity proxy, and the virial mass follows. In principle, it is elegant, and in practice it is a campaign of long monitoring and careful statistics. The monitoring itself is a kind of patience test. Night after night, telescopes gather spectra, building like curves that look like jagged heartbeats. Analysts cross-correlate the continuum and line variations, searching for the lag buried in uneven sampling and weather gaps. The measurement is not a single moment. It is a time-resolved experiment on a galaxy-sized distance. Reverberation mapping also exposes the complexity of the broadline region, because different lines respond with different lags. High ionization lines can respond quickly, implying they live closer in, while lower ionization lines lag behind, implying larger radii. The transfer function can be asymmetric, hinting at inflow, outflow, or disk-like geometry. The method measures a characteristic size, not a simple shell. That nuance matters, because a characteristic size is not a full map, and geometry is where systematics hide. If the emitting gas is clumpy, the response can be dominated by a few bright regions rather than the whole structure. If the illumination is anisotropic, some clouds may never see the flare that we see. Reverberation mapping is powerful, yet it is still an inference. The virial method requires a scale factor that encodes geometry, orientation, and the relationship between the observed line width and the true orbital speed. If the broadline region is a flattened disk, face-on systems show narrower lines than edge-on systems at the same mass. That orientation effect can bias masses low for some quasars and high for others, especially at the extremes. This is where the word biggest becomes slippery, because the most extreme objects may also be the most geometrically deceptive. A quasar viewed at an angle that minimizes line width can look modest, even if it is enormous. Another quasar with strong non-virial winds can look huge, even if the central mass is more ordinary. The spectrum is a witness, but not always a reliable one. Radiation pressure adds another complication in luminous sources, and it is not a small correction when the luminosity is near the Eddington limit. Intense light can push on broadline gas, altering its dynamics beyond pure gravity and changing the effective binding. Corrections have been proposed, but they depend on gas properties we do not fully know. At the top end, small systematic shifts can move a candidate in or out of the record book. The Eddington limit itself is a useful anchor, because it ties luminosity to mass through a balance of forces. When radiation pressure on electrons balances gravity, accretion becomes self-limiting, at least in simple models. A quasar's luminosity therefore hints at a minimum mass if it is not wildly super Eddington. Yet accretion physics is creative, and nature often finds ways to complicate simple limits. Because reverberation mapping is expensive, astronomers use it to calibrate faster tools, building a ladder of inference. Scaling relations connect broadline region size to AGN luminosity, based on empirical trends established from reverberation samples. If brighter AGN have larger broadline regions, then a single spectrum can estimate radius from luminosity. Single epoch mass estimates combine the inferred radius with a measured line width, and they are essential for huge surveys. They turn millions of quasars into a mass distribution, which lets us ask population questions about growth and cosmic evolution. They also carry systematic uncertainties from calibration, variability, extinction, and selection effects. The convenience is real, and so is the cost. Different emission lines introduce different biases, and the choice is often forced by redshift. H Beta is well studied at low redshift, but it shifts out of optical bands at high redshift, where many surveys operate. Mazusku and CF are used farther out, yet Cepheid can be contaminated by winds that broaden lines without indicating bound motion. The line choice can tilt the mass scale. Even the continuum luminosity is not a simple number, because it can be reddened by dust or boosted by beaming in special cases. Host galaxy starlight can contaminate the continuum at low luminosities, while absorption features can carve away flux in the ultraviolet. Analysts must model the spectral energy distribution, subtract components, and decide what the continuum actually is. Each decision is reasonable, yet each decision nudges the mass. The result is a ladder of inference that is sturdy in the middle and flexible at the top. At the bottom are dynamical masses in nearby galaxies, tied closely to gravity and geometry. Above that are reverberation masses, tied to time delays and calibrated scale factors. At the top are single epoch masses, fast and broad, but dependent on the lower rungs. The ladder is useful, but it is not rigid, and the rungs can shift as calibrations improve. Improved calibrations can move the entire quasar mass scale by tenths of a dex, which sounds small until you translate it into billions of solar masses. At the extreme tail, it changes which object appears biggest. The record is therefore partly about measurement culture, not only about nature. That culture has a history, and it is worth remembering how quickly the field has changed. A few decades ago, supermassive black holes were still debated as a class, and the evidence was pieced together from indirect clues. Then came Hubble Space Telescope kinematics, maser disks, and reverberation campaigns that turned suspicion into measurement. The modern argument is not whether they exist, but how massive the largest can be. The Event Horizon Telescope adds a different kind of constraint, and it is easy to misunderstand if we treat it like a normal telescope. The EHT does not weigh a black hole by watching stars orbit it, and it does not see the horizon as a crisp boundary. It images horizon-scale emission around nearby supermassive black holes using Earth-sized interferometry. The technique is itself a visual metaphor for inference. Radio dishes across continents record faint signals with atomic clock precision, and later those signals are combined as if Earth were one giant telescope. The reconstructed image is not a photograph in the everyday sense. It is a model constrained by sparse Fourier samples, yet the constraints are strong enough to reveal a ring-like structure. For M87, the EHT measured a ring-like structure consistent with strong lensing near the photon orbit. The angular size of that ring constrains the ratio of mass to distance, because gravity sets the physical scale for light bending. Combine it with an independent distance estimate, and mass follows with uncertainties. The result also cross-checks dynamical estimates from the galaxy's stars and gas. For SGRA, the EHT faced a different challenge because the source varies rapidly, almost as if the target refuses to sit still. The image is reconstructed from data that span changing emission, and that variability must be modelled rather than ignored. The resulting ring size again constrains mass to distance, and it agrees broadly with stellar orbit measurements from infrared astrometry. The key distinction is that the shadow size is not the horizon size, and neither is directly a mass. The observed ring depends on emission physics, viewing angle, and scattering along the line of sight, especially for SGR-AEN behind the Milky Way's turbulent plasma. The fundamental measurement is an angular scale tied to spacetime geometry, then translated into mass using distance. EHT results therefore complement rather than replace traditional weighing methods, and that complementarity is the point. They test whether the central object behaves like a Kerr black hole at horizon scales, where strong gravity leaves little room for imposters. They also reduce the space of allowed masses when combined with other data. Yet they are currently limited to a few nearby targets, not the faraway record contenders. In special cases, gravitational lensing can help constrain central masses, although the effect is subtle and demands exquisite data. A massive galaxy can lens a background source into multiple images, and the lens model depends on the galaxy's mass distribution along the line of sight. If the central potential is steepened by an overmassive black hole, it can affect image configurations near the core. These constraints are subtle and rare because lensing is dominated by the galaxy and its dark matter halo rather than by the black hole alone. Still, in a few systems, central image suppression and high-resolution lens modeling can place limits on the black hole. Lensing becomes another indirect ruler, useful when dynamics are inaccessible. It is a reminder that mass leaves fingerprints in geometry, as well as in motion. Host galaxy properties provide yet another line of inference, and they are both powerful and dangerous because they tempt us with easy answers. Black hole mass correlates with bulge velocity dispersion and bulge luminosity in nearby galaxies, relationships discovered and refined over years of surveys. If those relations hold broadly, we can estimate mass from host measurements even when the nucleus is faint. The correlations are suggestive because they hint at coevolution between black holes and their galaxies. A tighter bulge seems to come with a heavier central black hole, as if growth and feedback are linked across scales. Yet correlation is not a law, and the scatter is not a technicality. At the extremes, scatter is where the record claims live. But scaling relations have scatter, and the scatter may grow at the highest masses where galaxies are most unusual. Brightest cluster galaxies sit in dense environments with complex merger histories, and their stellar populations can be layered like geological strata. Their cores can be depleted by black hole binaries, altering light profiles and confusing dynamical models. The host can mislead when it is not typical. This is where the controversy over extreme masses often lives, because the data are good, but the modelling is fragile. Claims for tens of billions of solar masses in nearby giant ellipticals rely on stellar dynamical modelling at the edge of resolution. Small changes in assumed stellar mass-to-light ratio, dark matter halo profile, or orbital anisotropy can shift the best-fit black hole mass dramatically. Even the definition of centre can matter in these galaxies, because cores are shallow and kinematics can be complex. Triaxiality can break axis-emmetric assumptions used in many models, and a galaxy's true three-dimensional shape is hard to infer from a two-dimensional projection. If the galaxy is not shaped the way the model assumes, the inferred black hole can inflate to compensate. The monster grows in the gaps between assumptions. Orientation effects also haunt quasar-based masses, and they haunt them in a different way than they haunt dynamical models. A face-on broadline region can produce narrow lines that imply a smaller mass, even if the true mass is huge. A wind-dominated line can produce broadening that implies a larger mass, even if gravity is not the cause. The same spectrum can be read as two different stories. Error bars are therefore not just statistical, they are systematic, and the distinction matters for how confidence should feel. Statistical errors shrink with more photons and longer monitoring, and they behave like familiar noise. Systematic errors persist until models improve, and they can dominate at the top end where we have few calibrators. The biggest black hole is the place where systematics decide the podium. Selection bias then enters as the quiet antagonist of the chapter, because it shapes what we even call a candidate. We find what is easiest to find, and the easiest objects to find are bright, high-contrast sources. Quasars are selected by luminosity, colour and variability, which favours actively accreting black holes with high radiative output. But luminosity is not mass, and the two can be decoupled by accretion rate and radiative efficiency. A modest mass black hole accreting near the Eddington limit can outshine a larger black hole accreting weakly, like a small engine pushed to its redline. The sky's brightest beacons are not guaranteed to sit on the heaviest thrones. This creates a mass, accretion degeneracy in surveys, and it is not merely academic. If we see a luminous quasar, it could be extremely massive with moderate accretion, or moderately massive with extreme accretion. Single-epoch scaling relations try to break the degeneracy, but they inherit the same assumptions about geometry and calibration. The inference is fast, yet it is never free. Selection effects also shape the extreme tail by construction, because flux limits act like a filter on the universe. Flux limits mean we preferentially detect the brightest objects at a given distance, and distance itself dims light dramatically. At high redshift, we detect only the most luminous quasars, which biases the sample toward high inferred masses even if the true distribution is broader. The tail we see is not necessarily the tail that exists. There is also a survivorship bias in time, because quasar phases are episodic and we catch them mid-flare. We observe them during their bright phases, when accretion is active and the broadline region is well lit. The quiet giants, possibly more massive, can be missed because they do not advertise themselves. The biggest black hole could be a dark monarch in a dim nucleus, not a quasar lighthouse. Even when we do detect a candidate, the path from data to mass is a chain of conversions that can amplify small errors. Photons become spectra become line widths become velocities, and velocities become mass under assumptions about radius and geometry. Each link adds uncertainty, and the uncertainty compounds most at the extremes. The final number can look precise while hiding fragile dependencies, so the title of biggest becomes a question of which evidence is hardest to fake and which uncertainties are most honestly bounded. A nearby dynamical mass can be robust but limited by resolution and modelling choices. A quasar mass can be huge but rests on virial assumptions and calibration. The crown is contested because the crowns are made of different metals. Now we introduce the leading candidates, not as trophies, but as case files with strengths and vulnerabilities. TON 618 is the iconic quasar contender, with an enormous mass estimate derived from broad lines and luminosity scaling. It is compelling because it is bright, distant, and extreme, and it sits near the upper envelope of quasar mass catalogues. In visuals, TON 618 is a point of light that refuses to look like a point once you understand what it implies. Its spectrum is a forest of features stretched and blurred by velocity, and its continuum rises like a floodlight from the early universe. The host galaxy is mostly invisible behind the glare, which is part of the mystique and part of the problem. We are weighing a monster using the light of its meal. Yet TON 618 is also uncertain because its mass is not dynamical, and that distinction is decisive. Its estimate depends on which line is used, how the continuum is modelled, and what scale factor is adopted from reverberation calibrations. Orientation and wind contamination can shift the inferred velocity, and a small shift becomes billions of solar masses. The candidate remains extraordinary, but the error budget is part of the identity. On the local side, brightest cluster galaxies host candidates inferred from stellar dynamics, and their environments make the claim plausible. Objects like Holmberg 15A and other central cluster giants have been reported with very large masses in some analyses. They are compelling because they are nearby enough for dynamical work, and because their environments plausibly grow huge black holes through repeated mergers. A cluster core is a different kind of stage, and it changes what typical means. Galaxies fall in, interact, and merge over billions of years, and the central galaxy can become a repository of stellar debris. If black holes merge along with galaxies, the central black hole can grow in jumps rather than in smooth feeding. The environment supplies a growth channel that feels tailor-made for extremes. They are also uncertain because their cores are complex and their modelling is delicate, especially where the light profile flattens. The stellar light profile can be shallow, the dark matter halo can dominate, and the kinematics can be noisy or sparse near the centre. Different modelling choices can yield different masses, and the spread can be large enough to reorder the ranking. The same galaxy can host multiple biggest claims depending on assumptions. Some candidates sit in between, where both AGN methods and host constraints are available, and those cross-checks are valuable. A luminous nucleus can provide broad line estimates, while the host galaxy's dispersion provides a scaling relation check. Agreement strengthens confidence, but disagreement is common, and disagreement is information. It tells us where our ladders bend. Across all candidates, the chapter's theme is that measurement is detective work under constraints, not a single decisive test. We do not see the monster, we see its influence on matter and light, and we decide which influences are trustworthy. We build a case from multiple witnesses, and each witness has biases and blind spots. The biggest black hole may be both real and partly an artifact of how we look. This does not mean the quest is hopeless. It means the quest must be careful and intellectually honest. The goal is not to eliminate uncertainty, because uncertainty is intrinsic when the subject cannot be touched. The goal is to identify which candidate has the most converging lines of evidence, and which uncertainties are most honestly bounded. In a field of indirect rulers, integrity is part of the instrument. Armed with measurement tools, we can choose a destination without pretending the map is perfect, and we can explain why we choose it. We can decide whether to chase the brightest quasar beacons or the quiet giants in nearby cluster cores, where dynamics can be tested. We can also decide what biggest will mean in our story, and what evidence we will demand. Is it the highest best fit mass, or the highest mass that survives skepticism? That brings us to the documentary's next move. We will take the methods that survive skepticism, and we will follow them to the strongest candidate, not the loudest headline. Then we will push outward, because the farthest giants live where the universe was young and the clocks were fast. The mystery deepens when time itself becomes part of the measurement. We set course to the edge of the observable, toward quasar light that has travelled for most of cosmic history. If the biggest black hole is out there, it will be announced by a beacon, and weighed by the shadows in its spectrum. The farther we go, the more the universe forces us to measure with imperfect rulers, yet those rulers are all we have. To find the biggest, we have to learn how to weigh what cannot be touched and how to admit what we do not know. And once we can weigh it, we can finally decide which monster is worth the journey and which claims are only mirages at the edge of our methods. We set course to Ton 618, a quasar whose light has crossed most of cosmic history before reaching our instruments. It appears as a point in the sky, yet its spectrum announces an engine built from extreme gravity and relentless infall. It sits at high redshift, so every photon is also a timestamp, stamped when the universe was younger, denser, and still rapidly assembling structure. In the visual language of the documentary, the destination is not a place we can approach with engines. It is a faint bead of light against a deep black field, surrounded by quieter galaxies that look almost ordinary. Yet when we spread that bead into a rainbow, the rainbow fractures into sharp features, lines and breaks that carry physics. A quasar is an object we meet through analysis, and the analysis is how the universe lets us travel. Looking back in time is not metaphor, it is built into how light travels through expanding space. The quasar we measure is the quasar as it was billions of years ago, not as it is now in any practical sense. When we say distance, we also mean delay, because the speed of light turns the cosmos into a layered archive. The night sky becomes a time machine with no moving parts, and every observation is an excavation. Cosmic expansion stretches wavelengths while photons are in flight, and that stretching is written into the spectrum as redshift. A line emitted in the ultraviolet can arrive in our optical bands, and optical light can slide into the infrared, depending on how far it has travelled. Redshift becomes both a distance marker and a record of the universe's changing conditions. It is also a reminder that the universe is not static scenery. It is a dynamic stage that keeps changing during the journey. Historically, quasars were once a puzzle that looked like an error in the catalogue. In the early 1960s, radio sources were matched to star-like points, and their spectra did not fit any known stellar pattern. When the redshifts were recognised, the implied luminosities were shocking, and the word quasi-stellar became a placeholder for ignorance. The black hole interpretation, once radical, became the organising idea because it could power such brilliance without violating physics. Ton 618 matters because it lives near the upper edge of inferred black hole masses, where our methods are stretched and our assumptions become visible. It is not a quiet nucleus weighed by stellar orbits in a nearby galaxy, but a blazing accretion system weighed by indirect rulers. That difference makes it alluring and controversial in the same breath. The central darkness stays hidden, while the surrounding light becomes our evidence. The mass estimates for Ton 618 land in the tens of billions of solar masses, a number so large it risks becoming abstract. They come from quasar-virial methods that combine line width with an inferred broad-line radius. The calculation assumes the emitting gas is gravitationally bound and roughly virialized, meaning its kinetic energy and gravitational binding are in a stable relationship. It also assumes a geometry factor that folds in orientation and structure we cannot directly image. In practice, the method begins with a spectrum and a set of emission lines that act like speedometers. The broadening of a line is interpreted as Doppler motion, often thousands of kilometers per second, and that width becomes a proxy for orbital velocity. Then we need a radius, because gravity is not just about speed, it is about speed at a distance. The radius is inferred from luminosity through an empirical radius, luminosity relation, calibrated by reverberation mapping in nearer active galaxies. Reverberation mapping is one of the cleverest tricks in observational astrophysics, and it is worth feeling in the bones. The accretion disk brightens and dims, and the broad-line region responds after a delay because light takes time to cross the gap. That delay is a ruler, measured in days or weeks for nearby systems, and it turns variability into geometry. Once that ruler is established locally, it is extended outward to quasars too distant for direct time-lag campaigns. The range is not a technical footnote, it is the story's tension, because the uncertainty is part of the meaning. Different emission lines can yield different velocities because winds and stratification reshape profiles, and because not all gas is moving in neat circular orbits. Different calibrations of the radius, luminosity relations shift the inferred radius at fixed brightness. Even small systematic offsets in line width can move the mass by billions of suns. Ton 618 remains extreme, yet the crown is always conditional. We should be precise about what the number means in this context. because precision is the only honest way to speak about extremes. A virial mass is a best inference from a luminous environment, not a direct measurement of the horizon. It is anchored by reverberation mapping in nearer AGN, then extended to higher redshift with scaling relations that assume similar physics across cosmic time. The latter is credible, but its top rung flexes under the heaviest claims. That flex is why biggest becomes a question of meaning, not only arithmetic. There is also a subtle observational complication that hides in plain sight. Luminosity itself is not a simple candle. Dust can absorb and re-emit light, host galaxies can contribute starlight, and variability can shift a quasar's brightness between observing campaigns. Even the continuum we measure can be contaminated by broad emission blends that masquerade as baseline. Each correction is reasonable, yet each correction carries a choice, and choices accumulate at the frontier. Still, the implied scale is staggering, and scale is where intuition must be rebuilt with careful comparisons. For a non-rotating black hole, the Schwarzschild radius grows linearly with mass, a simple proportionality that feels almost too clean. Multiply the mass by 10, and the horizon radius grows by 10, with no extra complication. A tens of billions solar mass object therefore has a horizon comparable to solar system scales. The diameter can approach the size of the orbit of the outer planets, depending on the exact mass and the assumptions behind it. To visualize that, imagine placing the black hole at the Sun's position and drawing a sphere where escape becomes impossible. For stellar mass black holes, the sphere is smaller than a city, and it hides in the darkness of space. For TON 618's implied mass, that sphere becomes a region you could map with planetary ephemerides and deep space trajectories. The event horizon would not be a dot, it would be a domain. That scaling carries a counterintuitive consequence that the audience must feel. Bigger black holes do not have stronger tides at the horizon. They have gentler gradients there, even though the total gravity is enormous. Tidal forces depend on how quickly gravity changes across your body, not only on the overall pull. Near a supermassive horizon, the curvature can be spread over such a large radius that spaghettification is delayed. The danger is real, but the edge can be deceptively calm. This is one of general relativity's most unsettling lessons, because it separates force from geometry in a way everyday life never does. In free fall, you feel weightless even while gravity dominates your trajectory, because locally you are following a geodesic. What changes you, physically, is differential gravity, how neighbouring geodesics converge. For a giant horizon, those differences can be small at the boundary, even while the boundary is final. The calm is not safety, it is geometry and causality working together. Cross the horizon, and the future points inward, regardless of how gentle the entry felt in your own frame. The event horizon is not a surface you hit, it is a causal boundary you pass, defined by which signals can still reach infinity. This is where earlier chapters return with new weight, because the same rule scales up to monstrous sizes. TON 618 is a reminder that the boundary can be vast and still absolute. To understand why TON 618 shines, we step outward from the horizon into quasar anatomy, where the physics becomes luminous and measurable. Accretion begins with gas that cannot fall straight in because angular momentum blocks a direct plunge. The gas forms a disk, and the disk must shed angular momentum to feed the center, like a whirlpool that must lose spin to deepen. Magnetic turbulence acts like an effective viscosity, transporting angular momentum outward and letting mass drift inward. Gravitational potential energy becomes heat, and heat becomes radiation. The turbulence is not a vague metaphor, it is a specific instability that thrives in ionized, magnetized disks. The magnetorotational instability turns weak magnetic fields into tangled stresses that couple neighboring rings of gas. Those stresses transfer angular momentum outward, allowing inner material to spiral down and release energy. In plain terms, the disk finds a way to rub against itself without a solid surface. The result is a steady conversion of orbital energy into light. The disk is not one temperature, it is a gradient that maps distance from the center into color. Farther out, the disk is cooler and radiates in optical and infrared, often producing the bright continuum that first marks a quasar in surveys. Closer in, the disk becomes hot enough to radiate strongly in ultraviolet, where many of the ionizing photons are born. The inner edge sits near the innermost stable circular orbit, which depends on spin and on the spacetime geometry. Even without seeing the horizon, the spectrum carries hints of how deep the gas can orbit before it plunges. In visuals, the disk is a luminous whirl with a bright inner ring, fading outward into a broader, cooler glow. The inner regions flicker, not because the laws of physics change, but because the flow is turbulent and time-dependent. Hot spots shear apart, density waves propagate, and magnetic fields reconnect, releasing bursts of energy. The quasar's light is therefore not a steady lamp but a restless signal shaped by plasma physics. Above the disk sits the corona, a region of hot electrons that reshapes the light and adds a harder edge to the spectrum. Ultraviolet photons from the disk scatter off coronal electrons and gain energy through inverse Compton processes, stepping upward into X-ray energies. The result is X-ray emission, often variable and compact in origin, suggesting a small region close to the central engine. Those X-rays can illuminate the disk and produce reflection features, including broadened ion lines that encode strong gravity effects. In quasars as bright as TON 6/8 the corona becomes part of the mass and accretion story. The corona also raises a question that remains open in detail. How is it heated and sustained against rapid cooling? Magnetic reconnection, analogous to solar flares but far more intense, is a leading idea. In that picture, twisted magnetic fields snap and rearrange, dumping energy into electrons that then upscatter photons. The process links the disk's magnetized turbulence to the high-energy sky. It is another example of how microscopic plasma behavior can shape a cosmic beacon. Luminosity is not just spectacle, it is a measure of how fast the black hole is being fed and how efficiently gravity is being converted into radiation. The radiative output connects to accretion rate through an efficiency that depends on spin and disk structure, because deeper orbits release more energy before the plunge. If the efficiency is high, the quasar can shine intensely while gaining mass more slowly. If the efficiency is low, more of the inflowing mass can cross the horizon rather than escaping as light. The same brightness can therefore imply different growth histories. This is where the documentary can pause on a simple but profound idea. Light is the receipt for falling inward. Every photon is paid for by gravitational energy, and the bill is settled in the disk before matter disappears. In a sense, the quasar is a conversion machine, turning space-time curvature into radiation that can cross the universe. The brighter the quasar, the more aggressively it is tapping that reservoir. Yet brightness alone does not tell us how much mass is being added, because the conversion rate can change. The Eddington limit is the benchmark that turns light into a constraint, and it does so with a single balancing act. At the Eddington luminosity, radiation pressure on electrons can balance gravity for ionized gas in a simple spherical picture, because photons push on charged particles through Thomson's scattering. Real disks are not spheres, and real gas is not uniform, yet the limit still sets a characteristic scale for steady accretion. If TON 6/18 radiates near Eddington, it implies a sustained, heavy inflow over long periods. If it exceeds Eddington at times, it implies special accretion states that trap photons or channel outflows. It is important to say what limit means here, because the word can mislead. The Eddington value is not a hard wall that nature never crosses. It is a threshold where feedback becomes powerful and self-regulating. In thick disks, photons can be trapped and advected inward, reducing the effective outward push. In anisotropic emission, light can escape more easily in some directions than others, easing the constraint on inflow. The limit is therefore a guide to typical behavior, not a guarantee of simplicity. This is where TON 6/18 becomes a portal into early universe formation puzzles, because time is the resource that runs out first. At high redshift, there is less time available for repeated mass doublings, even if a black hole accretes efficiently. A tens of billions solar mass black hole pushes the arithmetic harder than a mere billion solar mass quasar, because each extra factor of 10 demands multiple e-foldings of growth. Either the seed was unusually massive, or the feeding was unusually persistent, or the accretion sometimes broke the standard speed limit. Each option carries consequences for how the first galaxies assembled and how their gas behaved. Massive seeds point toward direct collapse or other shortcuts in the first steps, where a large gas cloud avoids fragmenting into stars and instead forms a heavy black hole quickly. Near Eddington growth points toward long duty cycles in gas-rich halos, where the central engine stays on for a large fraction of cosmic time. Super Eddington episodes point toward thick disks where radiation is trapped and advected inward. letting mass pile on faster than light can push it away. Mergers can add mass in jumps, but they also risk recoil and disruption when gravitational waves carry momentum away. TON 618 does not choose one answer for us. It forces the question to stay open. The tension is sharpened by the fact that the early universe was not a quiet place. Gas was more abundant, mergers were more frequent, and the cosmic web was actively feeding halos along filaments. Yet feedback was also fierce, because young stars and growing black holes injected energy into their surroundings. The puzzle is not whether growth is possible, but how it remains coherent and sustained. TON 618 sits like a flag on the far edge of that possibility. The quasar spectrum adds another crucial layer, because it contains the broad line region, a luminous fog of fast-moving gas. This region sits outside the inner disk, where gas is photoionized by the central continuum and then re-emits at characteristic wavelengths. Emission lines are broadened by Doppler motion, often thousands of kilometers per second, and the broad wings hint at deep gravitational binding. The line width becomes a velocity proxy, and velocity is the first ingredient in virial mass estimates. The second ingredient is size, inferred from luminosity or, in nearer systems, from time lags. Different lines are not interchangeable, and that fact matters when we push to the extremes. Some lines are more affected by winds, some by absorption, and some by blending with neighbouring features. The gas is stratified, with higher ionization lines often forming closer in, where radiation pressure and outflows can be stronger. If a line is skewed or shifted, it may be telling us about a wind rather than an orbit. The spectrum becomes a layered narrative, and the mass estimate is a careful reading. Geometry matters because we see only a projection of motion, and projection can hide the true speed. If the broad line region is flattened, a face-on view produces narrower lines than an edge-on view at the same mass. If winds contribute, lines can broaden or shift without tracing bound orbits, and the shift can mimic velocity that is not gravitational. Different lines form at different radii, so they sample different kinematic zones. The mass estimate becomes a synthesis of physics and viewing angle, not a simple readout. This is why the geometry factor, often compressed into a single symbol, carries so much weight in the final number. It is a statistical correction built from populations, not a direct measurement of TON 618's specific structure. In a sense, it is where the universe refuses to give us a clean diagram. We can infer, compare, and model, but we cannot yet take a picture of the broadline region at that distance. The inference is powerful, yet it remains inference. Orientation also connects to another quasar feature that can dominate the story, the relativistic jet, even if TON 618 itself is not defined by one. Not all quasars launch powerful jets, but when they do, jets reshape their environments across enormous distances, carving channels through gas and lighting up radio lobes. Jets require organized magnetic fields and a way to extract energy from the central engine. One leading pathway is the Blandford-Znajek mechanism, where magnetic fields threading a spinning black hole tap rotational energy. The jet becomes a conduit from horizon-scale physics to intergalactic space. The mechanism is elegant because it treats the black hole not as a simple sink, but as a rotating object that can store extractable energy. In general relativity, spin drags spacetime around with it, and magnetic field lines anchored in surrounding plasma can be twisted by that frame dragging. The twisting launches electromagnetic energy outward along the rotation axis, accelerating particles to near light speed. The jet is then both a plasma flow and an electromagnetic structure, guided by fields as much as by matter. Jets form under specific conditions that are still debated, and the debate is part of the mystery rather than a flaw. The accretion flow may need to be geometrically thick or magnetically arrested, concentrating magnetic flux near the hole until the field is dynamically important. Spin likely matters, but spin alone is not enough without the right magnetic configuration and supply. When jets are present, they can heat circumgalactic gas, regulate cooling, and suppress or trigger star formation depending on how energy couples to the environment. They can also seed magnetic fields and turbulence in the intergalactic medium, leaving signatures long after the quasar fades. Even without a dominant jet, quasar winds can carry feedback outward, and winds are common enough to matter for interpretation. Radiation can drive outflows from the disk, especially when line opacity amplifies the push and gives photons more leverage. Those winds can broaden some emission lines and complicate virial interpretations because they add non-orbital velocities to the profile. They can also remove gas from the host, limiting future accretion and star formation. The quasar becomes both a growth phase and a self-limiting event. In imagery, winds appear as translucent cones or shells, streaming away from the bright disk like smoke pulled by an unseen draft. Absorption features in spectra, particularly blue-shifted ones, act like fingerprints of gas moving toward us. The same light that powers the wind also reveals it, because the wind imprints itself on the continuum. This is feedback made visible, a conversation between radiation and matter. The quasar shines, and the surrounding gas answers. TON 618 therefore sits in a cosmic setting, not in isolation, and the setting is part of why it exists at all. Quasars are biased tracers of massive dark matter halos, because only deep potentials can gather and cool enough gas early, despite heating and turbulence. A luminous quasar at high redshift implies a rare peak in the density field, the kind of region that the cosmic web feeds aggressively. It hints at a forming massive galaxy, likely surrounded by companions and filamentary inflows. The quasar is a signpost for where structure was assembling fastest. This environmental context connects to the broader story of galaxy formation, where gas supply and gravitational architecture decide what can grow. Massive halos can deliver cold gas along filaments, feeding central regions despite feedback, especially when streams penetrate hot atmospheres. Mergers are more common in dense regions, and mergers can funnel gas inward while also adding black hole mass. The same environment that grows a galaxy can also grow its central black hole, because both draw from the same reservoir. TON 618 becomes evidence that some regions of the early universe were exceptionally efficient at building central mass. There is a quiet implication here that is easy to miss. If TON 618 is real at this scale, it is not an isolated miracle. It suggests a population, perhaps rare, but physically allowed, shaped by the statistics of the early density field. It suggests that the upper tail of black hole growth is not empty, just difficult to sample. It also suggests that our surveys are catching only the brightest phases, the moments when accretion is most visible. How many giants are hidden in quieter states, masked by dust or low activity? Now we return to the horizon scale, because the audience needs the existential stakes, not only the astrophysical ones. Imagine a probe hovering near the event horizon of a supermassive black hole, with thrusters firing to resist the fall. Locally, physics feels ordinary, and the probe's clock ticks normally in its own frame, just as your wristwatch does. But signals climbing out lose energy, and their wavelengths stretch into redder and redder light. To a distant observer, the probe's transmissions slow and fade, approaching silence without quite reaching a final moment. The documentary can show this as a stream of pulses, initially crisp and bright, then gradually lengthening and dimming. Each pulse arrives later than the last, and each is shifted toward longer wavelengths, as if the universe is turning down the frequency knob. The probe is still sending in its own time, yet the outside world receives a dwindling echo. The horizon behaves like a one-way filter for information. The closer you hover, the more the outside universe steals your signal. Time dilation is not a trick of perception. It is a difference in how time is measured along different paths through curved space-time. Near the horizon, gravitational redshift becomes extreme, and the outside universe appears sped up to the hovering probe, because its own clock is deep in the gravitational well. The probe can watch distant cosmic history unfold rapidly, while it remains near the edge, seeing stars evolve and galaxies shift in accelerated montage, yet any attempt to escape requires enormous acceleration, because hovering is not free fall and demands constant thrust. The horizon is a boundary that can be approached, but not held casually. For a supermassive black hole, the story is stranger because the horizon is large, and large horizons change the human intuition of danger. The probe can cross the horizon without immediate tidal destruction, depending on how close it is to the center, and how the black hole's mass sets the curvature gradient. The crossing itself is not marked by a flash or a wall, and no alarm sounds in the laws of physics. The point of no return is defined by causality, not by impact. That is why we cannot see the central darkness directly, even in principle. This is also why the event horizon is such a powerful idea in science history, because it is both concrete and unreachable. It is defined by the behavior of light cones, by which future-directed paths can still lead outward. It is not a material surface, yet it behaves like a boundary in every operational sense. In the 20th century, the concept matured from a mathematical curiosity into a central feature of astrophysics. Quasars, with their immense power, helped force that maturation into the mainstream. The only thing we can observe is the light outside the boundary, and that light is tortured by gravity in ways that become measurable signatures. Photons are bent, delayed, blue-shifted and red-shifted as they climb and fall in curved spacetime, and their paths can loop in tight arcs near the photon sphere. The accretion flow converts gravitational energy into radiation with high efficiency. Yet the final plunge carries matter beyond any future communication. The quasar is therefore a visible shell around an invisible rule. TON 618 is a beacon that advertises the boundary while hiding what the boundary encloses. If we could stand far away and watch the inner disk, we would see a theatre of relativistic effects. One side of the disk would brighten due to Doppler boosting as it moves toward us, while the other side would dim as it moves away. Light would be lensed around the black hole, producing warped arcs and a faint ghostly ring. Even without a direct image, spectra and variability carry traces of this geometry. The universe gives us hints, but it rarely gives us clean pictures. This is where the documentary's central question sharpens again, because the object itself cannot be seen and the claim must survive scrutiny. What is the biggest black hole we can meaningfully talk about when the central object is hidden behind a causal boundary? Meaning comes from inference that survives skepticism, not from a single headline number. TON 618 is meaningful because it sits at the intersection of extreme luminosity, high redshift and plausible virial mass. It is also meaningful because its uncertainties are honest, and the debate is part of the measurement. We also have to acknowledge the competing giants that challenge the quasar crown, because the frontier is crowded with impressive claims. Nearby brightest cluster galaxies sometimes host dynamical mass estimates in the same tens of billions range, derived from stellar kinematics and the motion of gas. Those claims are grounded in resolved observations, but they depend on modelling choices in complex core-dominated galaxies where dark matter, stars, and black hole influence overlap. Quasar masses are easier to find at great distance, but they depend on broadline physics, calibration, and orientation. The contenders occupy different measurement regimes, and the regimes do not always agree. The comparison is not merely academic, because it reveals what we trust in different contexts. Dynamical measurements rely on spatially resolving the region where the black hole dominates, which is easier nearby but still challenging for the largest galaxies. Virial quasar measurements rely on interpreting light from gas we cannot resolve, which is feasible at high redshift but sensitive to structure. Each method has its own systematics, and systematics become decisive when we chase records. The biggest label, therefore, becomes a mirror of our methods, so the title of biggest may not belong to a single object in a permanent way, and permanence is not the point of science anyway. It may be a moving frontier shaped by new data, new calibrations, and new understanding of systematics. The upper envelope could contain several plausible champions, each with a different kind of evidence and a different kind of uncertainty. TON 618 embodies that frontier because it is both extreme and emblematic of how we weigh the far universe. The crown becomes a question we keep refining, not a trophy we lock away. Yet even as the ranking remains debated, the existence of such candidates is itself a profound constraint on cosmic history. Tens of billion solar mass black holes imply that gravity can assemble enormous curvature in finite cosmic time. Despite feedback and finite fuel supply, they imply sustained access to gas, or unusually massive seeds, or both. And they imply that the environment did not always shut growth down early. They imply that the early universe could build engines that outshone galaxies and still gained mass. They also imply that our theoretical models must remain flexible enough to accommodate rare extremes. TON 618 also reframes what approach means in this journey, because it forces humility about distance and resolution. We cannot travel to it in any practical sense, and we cannot resolve its horizon in an image, not with any foreseeable telescope. Our expedition is made of photons, spectra, and models that connect light to gravity. We approach by tightening inference, by cross-checking assumptions, and by translating brightness into mass and mass into geometry. The closer we get conceptually, the more the boundary dominates the story. In that sense, the quasar is a lesson in how modern astronomy works at its limits. We build a chain from detector counts to calibrated flux, from flux to luminosity, from luminosity to size, and from size and velocity to mass. Every link is tested against nearer objects where we can do more direct checks. Every link also carries a margin, and margins matter most at the top end. TON 618 is not only an object, it is a stress test. That brings us to the documentary's next move. To understand what it means to approach such an object, we must cross the boundary from observation into the physics of no return. We will leave the quasar's luminous machinery and focus on the horizon itself, where time, information, and causality become the main characters. The journey continues toward the edge that cannot be seen, only inferred from the light it torments. And as we go, we should keep asking what it means to know anything about a place that cannot send answers back. We have chased a record holder through spectra and scaling laws, yet the prize is a boundary that refuses to sit still. The central question tightens again, because the answer is not only a number. What is the biggest black hole we can meaningfully talk about when meaning ends at no return? We approach the biggest candidate as an outside observer first, because outside is where physics reports back in measurable signals. We do not see the horizon directly, so we build a portrait from proxies: light, timing, and motion. We measure accretion glow across the spectrum, from radio through optical into hard X-rays, and we watch how that glow changes. We measure polarized synchrotron light, which carries the fingerprint of magnetic fields twisting through hot plasma. We measure X-ray flicker from a compact corona, a region so small that its variability becomes a ruler. We measure jets when they exist, and we map how their power tracks spin and magnetic flux in the inner flow. In some galaxies, the jet is a thin, bright spear, and in others it is a broad, turbulent plume. Either way, it is a clue that the black hole is not only swallowing matter but also shaping it. The leading models suggest that rotating spacetime can help extract energy if magnetic fields thread the horizon region. The details are complex, yet the observational strategy is simple. Look for correlations between rotation, accretion state, and outflow power. We also measure gravity without touching it, because gravity writes itself into photon paths and travel times. Light bends around the mass, producing multiple images, warped arcs, and magnification that depends on geometry rather than on the source alone. When the alignment is close, the sky can form an Einstein ring, a near-perfect circle of distorted light. When the alignment is imperfect, the ring breaks into arcs, and those arcs become a map of curvature. In crowded fields, lensing can turn a single background galaxy into a mirrored set of crescents. Time delays appear when light takes different routes through curved spacetime, so the same flare arrives in staggered echoes. A brightening in the accretion flow can be seen directly, then seen again after a longer path that looped deeper in the gravitational well. Those delays are not merely a curiosity, because they encode distance and potential depth. In practice, observers build light curves, cross-correlate them, and look for the telltale lag pattern. The universe becomes a natural interferometer, with spacetime itself providing the extra path length. Near the horizon, the rules become operational rather than visual, because the boundary is not a surface you can point to. An event horizon is defined by causality, not by brightness, and it is global in time. It is the set of points whose future cannot reach distant observers, even if the local region looks calm. That definition sounds abstract, yet it has a sharp consequence. There exists a region from which no signal can ever escape. The horizon is not made of matter, but it behaves like a one-way gate in the causal structure. Real black holes are not perfectly static, and that matters for what we call a horizon in practice. Accretion changes the mass, and mergers shake the geometry, so the boundary can be dynamical rather than fixed. Even a steady trickle of gas adds energy, and energy is mass in general relativity. During a merger, the spacetime is violently time-dependent, and the notion of a clean, stationary edge becomes slippery. In these situations, the language of horizons becomes a toolkit rather than a single object. In practice, we often talk about apparent horizons, local trapped surfaces that can move as the spacetime evolves. A trapped surface is defined by what light does when it tries to leave. If both outgoing and ingoing light rays converge, rather than one expanding outward, the region is trapped. That is a local statement, and it can be checked without knowing the entire future. Numerical relativity codes, which simulate mergers, often locate these surfaces step by step as the geometry updates. The event horizon can only be located with knowledge of the entire future spacetime, which nature does not provide to any observer. The apparent horizon can be found locally, and it tracks what matter and light can escape right now. In an accreting system, these horizons can differ, yet they converge when the system settles into a quasi-stationary state. The distinction is not pedantic because observations are always made in real time. We infer horizons from behaviour, and behaviour depends on what is locally trapped, not on a completed history. As we close in, the strongest lensing happens near the photon sphere, where light can orbit in unstable loops. In the simplest non-rotating case, that orbit sits at a specific radius, and it is a precarious balance. A photon can circle once, twice, or many times, but any small nudge sends it either outward to freedom or inward to capture. In rotating spacetimes, the picture becomes richer, because prograde and retrograde orbits differ. The photon region becomes a warped shell shaped by spin and frame dragging. Photons can loop one or more times before escaping, creating a stack of higher-order images that pile up near the edge. Each additional loop adds path length, and each loop adds a delay, so the image is also a time machine of sorts. The result is a bright ring and a dark interior region that we call the shadow. On screen, it looks like a charcoal disc cut out of glowing fog, with a thin rim of fire around it. Yet the darkness is not paint, and the rim is not a physical ring. The shadow is not the horizon's outline, even when the image feels like a silhouette against a luminous background. It is the projection of unstable photon orbits and capture trajectories in curved spacetime. Its size and shape encode the metric, including mass and spin, more than plasma details. The plasma matters for brightness and texture, but the shadow's boundary is largely geometric. That is why the Event Horizon Telescope could compare images to general relativistic ray tracing models, even though the emitting gas is turbulent. This is why the biggest black holes are tempting targets for horizon-scale tests, even when they are unimaginably far away. Their horizons are enormous, so the angular scale can be measurable even at great distance. A larger mass means a larger Schwarzschild radius, and that translates into a larger apparent size on the sky. Their long dynamical times slow variability, giving instruments time to integrate and model. When the flow evolves slowly, the image becomes less of a snapshot and more of a stable measurement. There is also a practical advantage that is easy to miss. The larger the black hole, the lower the characteristic frequencies of its near-horizon dynamics. That means the same physical process, an orbit, a flare, a magnetic reconnection event, unfolds more slowly in our clocks. The universe gives us more time to watch, and that time can be converted into signal to noise. In a sense, supermassive black holes are slow-motion laboratories, yet even perfect imaging cannot reveal what the horizon hides, because the hiding is causal rather than technological. From far away, falling matter appears to slow, dim, and redshift as it approaches the boundary. Signals climb out with less energy, and the last photons arrive ever later, never quite declaring a final moment. The image can show matter getting closer and fainter, but it cannot show a crossing in finite external time. The horizon is not a wall that blocks light. It is a region from which light cannot reach us. That outside view is real, but it is not the whole story because it depends on the observer's slicing of time. For the infaller, proper time remains finite, and the horizon is crossed without infinite delay. General relativity insists that local physics in free fall remains ordinary at the crossing. The equations say that nothing singular happens at the horizon itself, at least for a large, uncharged, non-extreme black hole. The drama is postponed, and it is geometry that decides where it returns. This is the equivalence principle made dramatic because it turns a cosmic boundary into an almost mundane moment. A freely falling observer near the horizon should feel weightless, not crushed by a special force. For a supermassive black hole, tidal gradients at the horizon can be small, so the crossing can be uneventful. The same mass that makes the horizon huge also spreads out the curvature there. In plain terms, the edge can be gentle even when the interior is lethal. Tidal forces are the key physical quantity, because they measure how gravity changes across your body. They scale roughly with mass divided by radius cubed, and the horizon radius grows with mass. For very large black holes, that combination makes the gradient at the horizon surprisingly small. An astronaut could cross without being spaghettified at the boundary, even though spaghettification awaits deeper in. The danger is not the horizon itself, but the increasing curvature as the radius shrinks. The calmness is not comfort, because the geometry still turns the future inward. Inside the horizon, every future-directed path points towards smaller radius, like time itself becoming a coordinate of descent. The infaller can still look outward and see light from the universe, but cannot send light back. The outside sky can appear compressed and distorted, as if the universe is being funneled into a shrinking patch. Meanwhile, the ability to influence anything outside is gone, not by force, but by causal structure. Classical general relativity then offers a simple, unsettling split that is internally consistent. Outside observers can describe the horizon as a one-way boundary that stores no observable interior detail. Infallers describe no special drama at the crossing, at least until tides grow near the centre. Both descriptions are valid within their frames, and neither can be used to send a contradiction outward. The split is not a trick, but it is a warning about how viewpoint shapes narrative. That split becomes a paradox when quantum mechanics enters, because quantum theory demands unitary evolution for closed systems. Unitarity says information is not destroyed, even if it is scrambled beyond practical recovery. A horizon that permanently hides information threatens that rule, and the conflict becomes the information paradox. The paradox is not about whether we can decode the message, but about whether a message can be erased in principle. It is a clash between two pillars that have both been tested with extraordinary success. Before the paradox, we need the first quantum crack in black hole darkness, and it arrives from field theory. Hawking radiation arises when quantum fields are placed on curved spacetime with a horizon. The result is thermal emission to infinity, as if the black hole has a temperature. In the heuristic picture, vacuum fluctuations near the horizon can be separated by the causal boundary. One part of a correlated pair escapes while the other is trapped, and the escaping flux looks thermal. The deeper statement is that the notion of a particle depends on the observer and the spacetime geometry. What looks like vacuum to a freely falling observer can look like a bath of particles to an observer at infinity. The horizon changes the bookkeeping of modes, and that change shows up as radiation. Hawking's calculation was done in the 1970s, and it shocked the field because it welded quantum theory to gravity. It also implied that black holes have thermodynamic properties, not as metaphor, but as measurable quantities in principle. The temperature is inversely proportional to mass, so the biggest black holes are the coldest by far. A stellar black hole is hot by cosmic standards, though still faint compared to stars and even compared to many interstellar processes. A tens of billion solar mass black hole is colder than the cosmic microwave background, so it gains heat from the universe. In that regime, the black hole is not evaporating in any practical sense. It is absorbing more energy than it emits, like a cold stone in warm sunlight. Evaporation is therefore unimaginably slow for the biggest holes, far beyond any current cosmic timescale. The power output is tiny, and the mass loss per year is negligible even in the emptiest void. Yet the principle matters because it says black holes are not perfectly black, even in vacuum. It also implies that horizons are not just geometric boundaries. They behave like thermal objects, with temperature, entropy, and a kind of statistical mechanics. Hawking's result also forces thermodynamics into gravity, and the connection is precise rather than poetic. Black hole entropy is proportional to horizon area, not to volume. That scaling suggests the horizon counts microscopic degrees of freedom, as if the surface stores the information budget. Historically, this idea was foreshadowed by Jacob Bekenstein, who argued that black holes must have entropy to preserve the second law of thermodynamics. Hawking provided the temperature that made Bekenstein's entropy a full thermodynamic system. Area's entropy is not a decorative analogy. It is a quantitative law, with deep implications for how spacetime might be built. It hints that spacetime might be emergent, assembled from underlying quantum information rather than existing as a fundamental stage. It also suggests a holographic limit, where the maximum information in a region scales with its boundary. In plain language, the universe may store its deepest accounting on surfaces, not in volumes. That is a strange claim, yet it is supported by multiple lines of theoretical evidence. Now, the paradox sharpens into a specific contradiction that can be stated cleanly. If a black hole forms from a pure quantum state and then evaporates into thermal radiation, the final state looks mixed. Quantum mechanics forbids pure to mixed evolution in a closed system, so something must give. Either the radiation is not truly thermal, or the black hole leaves behind something, or the rules of quantum theory change. Each option carries a cost that propagates outward into the rest of physics. One option is information loss, which would modify quantum theory at a fundamental level and introduce true irreversibility. Another option is that information escapes in subtle correlations within Hawking radiation, even if the spectrum looks thermal at first glance. A third option is that the information is stored in remnants, though that creates its own problems with infinite state counts. The debate has lasted decades because each path threatens something we value. The paradox is not stubbornness, but a sign that we are missing a unifying principle. The modern framing uses entanglement and time because evaporation is a process, not an instant. Early Hawking radiation is entangled with the interior, so the radiation looks thermal and uninformative. As evaporation continues, the entanglement entropy of the radiation rises, then must fall if the final state is pure. This expected rise and fall is summarized by the Page curve, named after Don Page, who argued from statistical reasoning about typical quantum states. The curve is not a detailed model, but it is a consistency condition for unitarity. The turning point is called the Page time, when roughly half the entropy has been radiated away. After Page time, the radiation must begin carrying information out, in correlations that reduce entanglement with the interior. That requirement collides with the smooth horizon story, because entanglement cannot be freely shared. A quantum system cannot be maximally entangled with two independent partners at once, a constraint known as monogamy of entanglement. The paradox becomes a triangle that cannot close without breaking an edge. This is where complementarity enters as a proposed truce, and it does so by limiting what any observer can operationally confirm. It suggests that no single observer can verify both copies of information, so no measurable contradiction occurs. Outside observers can treat information as encoded on or near the horizon, while infallers experience a smooth crossing. The idea is not that both stories are simultaneously true in a naive sense. The idea is that the theory's predictions are consistent within each observer's accessible domain. Complementarity preserves unitarity for the outside description, and preserves the equivalence principle for the infaller's description. It accepts that the two stories cannot be combined into one global narrative without double counting. The horizon becomes a kind of translation layer between incompatible viewpoints. That translation is unsettling, because it suggests that where the information is may not be an absolute fact. It may be a statement that depends on the observer's causal access, but complementarity was challenged by the firewall argument, which tries to make the contradiction unavoidable with a sharper entanglement accounting. If late radiation must be entangled with early radiation to carry information, it cannot also be maximally entangled with interior partners. The entanglement needed for a smooth horizon would be broken, so the infaller would meet high-energy quanta at the horizon. The horizon would become a place where quantum fields are violently excited rather than quiet vacuum. The argument is designed to corner the theory into choosing which principle to abandon. A firewall is not a small correction, because it replaces calm crossing with violent destruction at the boundary. It preserves unitarity by sacrificing the equivalence principle at the horizon. It turns the horizon into a physical surface, even though classical general relativity insists it is not. Visually, it is a shocking idea. A thin, invisible shell of lethal energy where the equations once promised emptiness. If it exists, it would mean that the smoothness of spacetime is not guaranteed, even at low curvature. Other ideas try to avoid that price by changing what we mean by interior and exterior, while keeping unitarity intact. Some proposals replace the classical interior with quantum structure, like fuzzballs, where microstates fill the would-be interior. In that picture, there is no empty region behind a horizon in the classical sense. Others suggest that spacetime connectivity and entanglement are linked, so the interior is encoded in correlations rather than in an independent volume. The common theme is that classical geometry may be an emergent description that fails in the most extreme bookkeeping. A newer, more concrete development is the idea of entanglement islands, which emerge from calculations where quantum gravity effects can be controlled. In certain models, the region that contributes to the entropy of Hawking radiation includes parts of the interior. The radiation's entanglement entropy then follows the Page curve without requiring a firewall, at least in the setups where the math is reliable. The surprising move is that the subsystem whose entropy we compute is not defined only by naive spatial separation. The gravitational path integral changes the effective partition of degrees of freedom. In accessible terms, Islands suggest that what counts as the radiation's information is not limited to what is far away. Quantum gravity can reorganize which degrees of freedom belong to which subsystem, even when classical geometry would separate them. The boundary between inside and outside becomes less absolute in quantum theory than in classical spacetime diagrams. That does not mean anything can escape causality in the ordinary sense. It means the accounting of information can be non-local in a way that still respects the theory's deeper rules. This does not resolve the paradox in everyday language, but it changes the shape of the problem and narrows the space of consistent stories. It suggests that the horizon is not merely a curtain, but a bookkeeping rule for information. It also suggests that the classical picture of a fixed interior may be an approximation that fails when quantum effects are included. The unsettling question becomes more precise. What is the interior if the theory can reassign it? And what does where even mean when geometry is part of the quantum system? The biggest black holes matter here because they separate timescales cleanly, which is a gift to both theory and observation. Their horizons are large, so curvature at the edge is small, making classical predictions robust locally. Their evaporation is negligible, so Hawking radiation is conceptually crucial, but observationally inaccessible, forcing indirect tests. This combination is almost perverse. The cleanest horizons for classical smoothness are the least helpful for seeing quantum leakage. The paradox becomes a thought experiment that nature hides behind enormous patience. That tension is part of the chapter's mystery, because it forces us to test quantum gravity without the obvious quantum signal. The smallest holes would radiate most strongly, but they are rare and hard to confirm, and they may not exist in nature today. Primordial black holes remain speculative, and even if they exist, their masses and abundances are constrained. So we turn to the giants, and we ask a different question. If quantum structure exists near horizons, can it leave faint classical fingerprints that accumulate over time? Still, supermassive holes can test quantum gravity in another way, through precision classical signatures that are sensitive to near-horizon structure. If quantum structure modifies the near-horizon region, it might produce echoes or deviations in gravitational wave ring down. It might also alter the shadow shape at a subtle level, or shift the photon ring's fine structure. These are small effects, and that is the point. When general relativity makes a crisp prediction, even a tiny deviation becomes meaningful. Gravitational waves give us a new probe because they carry the spacetime's own vibrations, not merely light emitted by matter. After a merger, the remnant rings like a bell, emitting quasi-normal modes. The frequencies and damping times depend only on mass and spin in general relativity, which is the essence of the no-hair theorem. The early part of the signal is a violent chirp, driven by orbital motion and plunge. The later part is a clean, decaying tone, as the remnant settles into Kerr. Ring-down spectroscopy therefore becomes a test of whether the remnant is a Kerr black hole, as the theory insists. If multiple modes are measured, they should fit one consistent mass and spin. Deviations could indicate exotic compact objects, modified gravity, or quantum corrections near the horizon. The challenge is that the modes can be faint and short-lived, especially for stellar mass mergers. Yet the principle is powerful, because it turns a single event into a measurement of spacetime's allowed resonances. The biggest black holes are also central targets for space-based gravitational wave detectors, which listen in a lower frequency band. Massive black hole mergers produce lower frequency waves that ground-based detectors cannot hear. A detector like LISA can track and spiral for months, measuring parameters with high precision and testing strong field dynamics. Months of data allow us to watch precession, eccentricity, and subtle phase shifts that encode relativistic effects. The inspiral becomes a long conversation between two masses and the geometry they create. Spin becomes a key variable in these tests because spin reshapes the horizon and the photon region in measurable ways. High spin changes the innermost stable orbit, changes accretion efficiency, and changes jet power. It also changes the ring-down spectrum, giving more handles for consistency checks. In images, spin can shift brightness asymmetry through Doppler boosting and frame dragging. In waves, spin changes the phasing and the final remnant's mode frequencies. The same parameter leaves signatures in light and in gravity. Now we return to horizons again, because the word hides more than one concept, and observations must choose the usable one. In dynamical spacetimes, an apparent horizon can form and move even when the global event horizon is hard to define. Observationally, we infer horizons from behavior of matter and light, not from a God's eye map of spacetime. We see matter disappear from view, we see emission truncate, and we see trajectories bend into capture. These are empirical signs of a trapped region, even if the exact global boundary is unknowable. This matters for cosmic censorship, the conjecture that singularities are hidden behind horizons so that predictability is protected. If censorship holds, nature keeps naked singularities out of view, and classical evolution remains well posed for distant observers. If censorship fails, then regions of arbitrarily strong curvature could be visible, and classical evolution could lose uniqueness. The conjecture is a guardrail, not a theorem, and it is tested in the hardest regime. It is also a statement about what the universe allows us to see. A naked singularity would not just be a brighter black hole, it would be a different kind of object with different causal structure. It could produce unusual lensing patterns, altered accretion dynamics, and potentially different gravitational wave signatures. The absence of a horizon could allow matter to orbit closer to the central region, changing efficiency and variability. The lensing could lack the familiar shadow structure, or replace it with a different central brightness profile. Observationally, it would mean the universe allows exposed breakdowns of classical physics. Cosmic censorship is not proven, and it is not merely philosophical, because it shapes what counts as a predictable universe. Numerical relativity suggests that many realistic collapses do form horizons, yet special setups can push toward extremality. Extreme spin and charge are limited in astrophysics, because charge neutralizes and accretion can torque systems away from perfect extremality. Mergers can transiently explore near-extreme regimes, though, and those transients are where the conjecture is stressed. The edge cases are not typical, but they are informative. The biggest black holes, especially in dense environments, may approach high spins through coherent accretion over long periods. They may also experience repeated mergers that randomize spin, depending on the history of the host galaxy. Either way, measuring spin distributions becomes part of testing how close nature gets to the edge of censorship. A population of near-extremal spins would suggest long, ordered feeding. A broader distribution would suggest chaotic growth and frequent mergers. The statistics become a narrative of cosmic history written in angular momentum. At this point, the chapter's climax is clear, because the horizon has become more than a line on a diagram. The horizon is both a geometric boundary and a thermodynamic object, and it forces quantum theory into the story. It is where time dilation becomes operational, where information becomes contested, and where the meaning of interior becomes uncertain. The same boundary that makes black holes simple in classical theory makes them profound in quantum theory. The simplicity is deceptive, and the deception is productive. We can now stage the guided approach as a final sequence of what can and cannot be known, with the camera staying outside. Outside, we can map the accretion flow spectrum, polarization and variability, and we can model lensing and time delays. Outside, we can measure the shadow and photon ring, and we can test whether the geometry matches Kerr. Outside, we can compare images across frequencies, looking for consistent ring diameters and consistent spin signatures. Each wavelength adds a layer, like different filters revealing the same underlying structure. Outside, we can listen to mergers through gravitational waves and read ring down as spacetime spectroscopy. Outside, we can infer mass and spin with multiple methods and cross-check them against each other. We can compare stellar dynamics, gas dynamics, mesodisks and reverberation mapping and ask whether they agree. We can compare those masses to lensing constraints and to gravitational wave measurements when available. Yet outside, we still cannot retrieve a message sent from within the horizon because the causal structure forbids it. The limit is not sensitivity, but the direction of time-like paths. Inside, classical general relativity predicts a smooth crossing for an infailure, especially for a supermassive horizon with weak curvature at the edge. Inside, the infaller's local physics remains ordinary until tides grow, and no local experiment detects the horizon as a material wall. A falling laboratory can measure local fields, atomic transitions, and the behavior of clocks, and find nothing special at the crossing. Inside, the future ends at a singularity in finite proper time, at least in the classical equations. The interior is not a place you can avoid, because it is the destination of all future-directed motion. Quantum theory refuses to let the story end there, because it demands a consistent accounting of information and a consistent evolution of states. Hawking radiation implies horizons have temperature and entropy, so the boundary has microscopic meaning. The information paradox implies that either the horizon is not smooth, or the interior is not independent, or quantum mechanics must be revised. Each possibility is a radical statement about what spacetime is. The paradox persists because every resolution seems to demand a new sacrifice. Firewalls, complementarity, fuzzballs, and islands are not just competing buzzwords, and they are not merely fashions in theoretical taste. They are different ways of choosing what to preserve when cherished principles collide. One preserves smoothness, one preserves unitarity, one preserves locality, and none preserves everything without cost. The proposals can sound abstract, yet they are anchored in concrete constraints like entanglement monogamy and thermodynamic consistency. The horizon is where those constraints meet, and where they argue. The biggest black holes become laboratories because they stretch the separation between curvature and horizon size in a way no other objects can. They give us vast, gentle horizons where classical smoothness should be safest. They also give us long-lived systems where tiny deviations could accumulate into measurable signatures if we learn where to look. A subtle modification of a ring down might be easier to see when the signal is long and clean. A subtle modification of photon ring substructure might be easier to see when the target is stable. Yet the philosophical sting remains, because the horizon is a boundary of knowledge as well as motion. If information can be hidden, then reality may be observer-dependent in a deeper way than relativity already taught us. If information cannot be hidden, then the horizon must be more than a one-way door. It must be a dynamic interface that releases information without violating causality in any ordinary sense. The question becomes less about escape velocity, and more about the architecture of quantum spacetime. The central question returns with a new meaning, and it circles back to what biggest really buys us. The biggest black hole is not only a mass to rank, it is a regime to interrogate. Its existence forces us to ask what counts as a physical fact, when different observers cannot agree on what is accessible. Does the universe permit facts that are real but forever unreportable? Or does quantum theory demand that all facts be, in some encoded way, recoverable? That brings us to the documentary's next move. After confronting the horizon's puzzles, we zoom back out to the cosmic role of these giants. We ask how they shape galaxies and clusters, and what biggest means in a universe still evolving. The horizon is an edge in spacetime, but it is also a hinge in cosmic history. The same object that hides information can sculpt the visible universe through feedback and gravity. We leave the edge of no return with a final tension unresolved by design. The horizon looks smooth in classical theory, yet it behaves like an information surface in quantum theory. The biggest black holes do not end the argument. They give the universe enough scale and time for us to test it, and enough mystery to keep the question sharp. We return to the central question with a final constraint. Biggest is not one number, because black holes are inferred through different kinds of evidence. In practice, each method touches a different layer of reality: light, motion, geometry, or aftermath, and each layer carries its own biases. In this series, we treated black holes as geometry first, then as engines, and that choice matters now because geometry defines what we can measure cleanly. When we say black hole, we are naming a space-time solution with an event horizon, not a glowing object we can hold up beside another. One meaning of biggest is most massive, because mass sets the curvature scale and the depth of the gravitational well. For a non-rotating hole, mass also sets the horizon radius in direct proportion, giving a simple ruler that is elegant on paper. In that Schwarzschild case, the radius is about 3 kilometers per solar mass, which sounds small until the numbers become cosmic. Multiply by 1 billion suns, and the horizon swells to a size comparable to the orbit of planets, yet the edge still looks deceptively calm. Another meaning is largest horizon radius, which tracks mass but depends slightly on spin and on which horizon you mean. A fast-spinning Kerr hole has a smaller outer horizon than a Schwarzschild hole of equal mass, because rotation reshapes the space-time. Spin does something else that is easy to miss in casual rankings. It changes the effective size of the central engine. The ergosphere appears, frame dragging becomes unavoidable, and the region where energy can be extracted expands even as the horizon contracts. Another meaning is most luminous active galactic nucleus, which tracks accretion power rather than the hole's bare mass. Luminosity can be boosted by beaming, and it can be throttled by dust, orientation, and the messy geometry of gas close to the centre. A quasar can look like a single point of light, yet it is a layered structure, a hot inner disk, a broader line-emitting region, and a dusty torus farther out. The same system can appear brilliant or muted depending on whether we see down the funnel or through the smoke. Another meaning is fastest spin, which changes the innermost stable orbit and therefore the efficiency of turning mass into light. Spin is inferred from spectra, polarization, and timing, and it remains model-dependent because the disk is not a rigid laboratory. When spin is high and aligned, the innermost stable orbit moves inward, and the disk can radiate more per kilogram of infalling gas. That efficiency shift matters because it sets how quickly a black hole can grow for a given fuel supply. Another meaning is most influential feedback, which is measured in consequences rather than in intrinsic properties. Jets and winds can reshape gas far beyond the sphere of influence, leaving cavities, shocks, and chemical fingerprints that persist long after the nucleus dims. Mass is the cleanest category in principle, because it is a property of the spacetime and not a mood of the accretion flow. Mass is also the hardest at the extreme tail, because the best rulers fail at distance, and because the most massive candidates are often the farthest. So what is the biggest black hole we can meaningfully talk about today? The honest answer is conditional, and the conditions are the measurement method and the definition, which is why headlines can mislead even when the underlying science is careful. By widely cited quasar-virial estimates, TON 618 remains a leading contender, and it has become a kind of shorthand for the extreme end. Many analyses place it in the tens of billions of solar masses, with substantial systematic uncertainty that is inseparable from the method. TON 618 is compelling because it is bright, distant and extreme, like a lighthouse seen across a stormy ocean of intervening space. It is also fragile because its mass comes from broad-line widths and radius scaling relations, which are powerful but indirect. Those relations are calibrated on nearer active galaxies using reverberation mapping, where we watch light echoes ripple through the broad-line region. A flare in the continuum is followed by a delayed response in emission lines, and that time lag becomes a physical distance. The logic is simple in plain language. Measure how long the echo takes, then combine that size with the gas speed to infer the central mass. The complication is that the broadline region is not a neat ring, and its geometry is inferred statistically. At high luminosity and high redshift, the top rung flexes under selection effects, because we preferentially discover the brightest objects. The quasars that make it into catalogues are not a fair sample of all black holes. They are the ones caught in a rare radiant phase. Line choice matters because some lines trace winds as much as gravity, and winds can broaden profiles without adding mass. Orientation matters because a flattened broadline region projects different velocities onto our sightline, turning the same system into different numbers. Radiation pressure and non-virial motions can bias the inferred mass upward or downward, depending on how gas responds to the glare. Small shifts in calibration become billions of suns at the frontier, where the scaling relations are stretched to their limits. There is also a deeper astrophysical tension hiding inside the uncertainty. If the mass is truly enormous, the black hole had to grow quickly in cosmic time. If the mass is smaller, the growth story relaxes, but then the quasar's brilliance demands a different explanation. Meanwhile, the strongest dynamical candidates live nearby in brightest cluster galaxies, where we can watch stars and gas move under gravity's command. Their masses are inferred from stellar and gas dynamics in complex core-dominated systems, often embedded in sprawling halos. These dynamical claims can also reach the tens of billions of solar masses, and they carry a different kind of credibility because they rely on motion. They depend on resolving the sphere of influence and modelling stars, dark matter and anisotropy with enough realism. The sphere of influence is the region where the black hole's gravity dominates over the surrounding stars, and it shrinks in angular size with distance. Even for a giant black hole, that region can be smaller than a pixel unless the galaxy is close and the telescope is sharp. In giant ellipticals, the black hole competes with a dense stellar core and a massive halo, and the light profile can be deceptively smooth. Degeneracies can masquerade as extracentral mass if the model is incomplete, especially when orbital families are not fully captured. Gas dynamics bring their own traps, because gas can feel pressure, turbulence, and magnetic forces in addition to gravity. A disk that looks orderly can hide non-circular motions, and a small warp can mimic the signature of a heavier central object. So the record is not a single throne, and it may not be stable, because each new dataset tightens one error bar while revealing another. The best we can say is that multiple objects plausibly occupy the same extreme tier, and the ordering is still being negotiated. If we must name a headline candidate, TON 618 is still the iconic one, partly because it sits at the intersection of distance and power. If we must name the caveat, the crown depends on assumptions we are still testing, and those assumptions are not minor details. That brings us to the deeper resolution of the documentary. The biggest black hole is not only a target, it is a stress test for how we know. Because the extremes expose every hidden approximation in our methods. We now zoom out from the candidates to the universe that makes them possible, and the visual should widen with the narration. Supermassive black holes are not isolated monsters, they are nodes in the cosmic web, embedded where matter streams converge. Dark matter halos assemble first, drawing baryons into deepening potential wells, and this hierarchy was recognized long before we could simulate it in detail. Gas cools, forms stars, and funnels inward through instabilities and mergers, while angular momentum acts as both barrier and guide. Mergers build galaxies, and they also build black holes, sometimes by adding mass directly when two central holes finally coalesce. More often they drive gas inward, feeding accretion that grows the central object, and they disturb disks enough to trigger inflows over many scales. The early universe was dense, filamentary, and merger-rich, which helps growth by providing frequent encounters and abundant cold gas. The same era also imposed limits through feedback, finite fuel, and radiative self-regulation, because an engine that shines too hard can blow away its own supply. The existence of tens of billion solar mass candidates tightens the growth puzzle, because the clock is set by cosmic expansion. Either seeds were heavy, accretion was sustained, or some phases exceeded simple Eddington expectations, at least in an effective time-average sense. The Eddington limit is a balancing act between gravity pulling inward and radiation pushing outward, and it sets a characteristic timescale for exponential growth. It is not an absolute speed limit in every geometry, but it is a powerful baseline that makes extreme masses feel surprising. Direct collapse seeds offer a shortcut by starting large in metal-poor environments, where cooling and fragmentation can be suppressed. Super Eddington episodes offer a shortcut by trapping radiation and letting mass flow faster than light escapes, especially in thick funnel-shaped disks. Long duty cycles offer a shortcut by keeping the engine on for a large fraction of time, rather than flickering rarely. Mergers offer a shortcut by adding mass in jumps, while risking recoil and disruption, because gravitational wave kicks can displace the remnant from the galactic center. None of these pathways is exclusive, and the universe likely used several, depending on environment and epoch. The biggest candidates are therefore clues to the rarest assembly histories, those unusual sequences of fuel, timing, and geometry that beat the typical constraints. As structure grows, black holes do more than gain mass, and the documentary's tone should shift from inventory to consequence. They return energy to their surroundings, and that feedback becomes part of cosmology, because it changes how gas behaves on galactic and cluster scales. Jets and winds inject heat and momentum into circumgalactic and intracluster gas, and the effect can be visible even when the nucleus is not. They can inflate cavities, drive shocks, and stir turbulence over hundreds of thousands of light years, sculpting X-ray bright atmospheres like weather systems. In clusters, feedback can regulate cooling flows by preventing gas from condensing too quickly, which would otherwise rain onto the central galaxy. Without that heating, many cluster cores would form stars at rates we do not observe, and the mismatch would echo through models of galaxy evolution. In galaxies, outflows can clear gas from the central regions and quench star formation, leaving red, quiet stellar populations behind. They can also compress gas in shells and trigger bursts, depending on coupling and geometry, so the same engine can both suppress and provoke. This is why black holes appear in scaling relations with their host galaxies, linking black hole mass to bulge properties in a way that feels too tight to be accidental. Coevolution is not a slogan. It is the imprint of long-term energy exchange, integrated over billions of years. The biggest black holes may therefore be the biggest feedback engines, even when they are quiet now, because the past can dominate the present. A dormant giant can still sit in a hot halo shaped by ancient eruptions, like a cratered landscape that remembers an old impact. Here the definition of biggest shifts again from mass to influence, and influence is harder to rank because it is contextual. It depends on environment, duty cycle, and the history of coupling, and it forces an uncomfortable question. Are we measuring the whole or the story around it? We also confront the limits of what we can see in the observable universe, because observation is filtered by selection. The farthest quasars are visible because they are bright, not because they are typical, and their very detectability is a kind of bias. Selection effects bias us toward luminous accretion phases and against quiescent giants, which may dominate the true census. Obscuration biases us against dust-enshrouded growth, especially in the early universe, where gas fractions were high and galaxies were messy. So it is plausible that even larger black holes exist than our current champions, and the thought is not extravagant. They may be inactive, hidden in massive galaxies, or buried behind gas and dust, leaving only subtle dynamical signatures that are hard to extract. Measurement systematics also widen the uncertainty at the top end, because the methods are stretched beyond their comfortable calibration range. In quasars, the broadline region is unresolved and its geometry is inferred statistically, which means we're always one assumption away from a shift. In dynamical galaxies, the modelling depends on assumptions about orbital structure and dark matter, and those assumptions can trade off against the central mass. At extreme masses, small modelling choices can change the answer dramatically, because the data are fighting multiple components at once. So the biggest known black hole is a moving boundary, not a final fact, and that is the correct posture for frontier science. The provisional nature of the answer is not weakness, it is the method working, because uncertainty is how knowledge stays honest. That brings us to the biggest idea, which is what black holes reveal about the universe. They are where gravity becomes geometry, and geometry becomes a limit on knowledge, because the rules of measurement are written into the shape of spacetime. The event horizon is locally unremarkable for an infala, yet globally absolute for communication, and that contrast is one of nature's sharpest tricks. The split forces us to define what we mean by observation and by reality, because seeing becomes a statement about causal structure. The horizon also turns thermodynamics into a property of spacetime, which would have sounded like philosophy before the 1970s. Hawking radiation and Bekenstein entropy say, the boundary has temperature and an information budget, even though the classical horizon is defined by no return. That entropy scales with area rather than volume, a clue that spacetime may store information in a holographic way. The plain language version is unsettling. The bookkeeping of a region might live on its boundary, as if the universe prefers surfaces to interiors. The information paradox then turns the universe into a riddle about unitarity and locality, because quantum theory dislikes permanent loss. Proposed resolutions reshape what we mean by inside, outside, and even spacetime itself, and they hint that horizons are not merely edges but active participants. Cosmic censorship remains a gatekeeper in the background, because predictability depends on hidden singularities rather than exposed ones. Extreme spins and mergers test the edge cases where censorship could fail, and where the equations might reveal naked breakdowns of classical order. The biggest black holes sharpen these issues by giving us vast horizons with low curvature at the edge, making the classical picture feel almost gentle. They make the classical story clean locally, while leaving quantum questions unavoidable, because the global causal boundary still exists. In that sense, the biggest black hole is also the biggest question mark, and the documentary's mystery deepens rather than resolves. It is a boundary where everyday ideas of time, space, and information begin to fail, not by drama, but by definition. Now we look forward, because the frontier is about to change, and the visuals should shift from archival to anticipatory. New tools will not only find bigger candidates, they will tighten what meaningfully talk about can mean, by shrinking uncertainties and cross-checking methods. Extremely large telescopes will resolve stellar dynamics in more distant galaxies, pushing the dynamical method beyond the local neighbourhood. Better angular resolution and spectroscopy will expand the reach of dynamical mass measurements, letting us separate the black hole's pull from the galaxy's broader mass distribution. Improved reverberation mapping will calibrate the broadline region across luminosity and redshift, reducing the need to extrapolate from nearby, modest systems. Longer monitoring and better cadence will reduce reliance on single-epoch scaling, and multi-line campaigns will help disentangle winds from virial motion. Next-generation Event Horizon telescope arrays will sharpen images of shadows and photon rings, turning geometry into a direct observable for more targets. Multi-frequency imaging and polarization will test Kerr geometry and accretion physics together, because magnetic fields leave patterns that mass alone cannot explain. Space-based gravitational wave observatories like LISA will open the massive black hole merger band, adding a new sense to astronomy. In spirals and ringdowns, we'll measure masses and spins without relying on light, and they will do it through the rhythm of spacetime itself. Those waves will also test the no-hair prediction through ringdown spectroscopy, comparing observed modes to the Kerr template. Any persistent deviation would point to new physics near horizons, or to unexpected structure in what we thought was a simple, bald object. The future may therefore reveal a larger black hole than TON 618, or a larger one than any cluster galaxy, and it may do so with multiple methods agreeing. It may also reveal that our categories were incomplete, because nature often refuses to fit inside our neat labels. Because biggest is not only about mass, it is about what can be inferred reliably, and reliability is earned through redundancy. The best answer may become a confidence interval, not a single champion, and that would be progress rather than anticlimax. We end where the series began, with a simple hook that became a philosophy, and the final images should slow down. Somewhere gravity has grown so powerful that it rewrites time and hides a cosmos behind a one-way boundary, and yet we still try to measure it from the outside. The quasar light that guided us is real, and it is also a message about limits, carried across expanding space. It tells us how much can be known from outside and how much remains sealed by causality, no matter how perfect our instruments become. As the light fades, the darkness does not feel empty anymore, because we have learned what the darkness can contain. Space is not a stage, it is a fabric that can fold into horizons, and those horizons fold back into our theories, forcing revisions that feel both mathematical and philosophical. The journey to the biggest black hole becomes a journey to the edge of explanation, where measurement meets meaning. The universe does not only offer record holders, it offers boundaries that demand new rules, and it asks us whether biggest is a property or a relationship. And the final answer is deliberately unfinished, because the horizon is always ahead, both literally and intellectually. The biggest black hole we can name today is provisional, and the biggest idea is still forming, waiting for the next observation to sharpen its outline. We began by retiring the myth of the cosmic vacuum, and found something stranger than a mouth in space, a shape in space-time that only captures what cannot keep its balance. We followed that shape from collapsing stars to galactic thrones, watching accretion disks and jets blaze outside the horizon, while the horizon itself stayed dark, silent, and definitional. Along the way, we learned that every measurement of a black hole is really a measurement of its gravity's fingerprints. Stellar orbits, massive disks, broadened lines, reverberation echoes, lensing arcs, and the EHT's ring, each powerful, each biased, each incomplete. When we pushed toward the extreme tail, the story became less about a single champion, and more about a contested frontier, where TON 618's enormous mass is plausible, yet inseparable from calibration choices, orientation, winds, and selection effects. The early universe growth tension never fully relaxes, it simply sharpens, forcing us to weigh Super Eddington episodes, heavy seeds, mergers, and long duty cycles against the stubborn bookkeeping of radiation pressure and fuel. And at the edge of no return, the deepest revelation was not what shines, but what cannot be returned. An event horizon that can feel locally ordinary, even gentle for a supermassive infaller, yet remains globally absolute as a one-way rule for information. In that split between what falls and what watches, time itself becomes part of the evidence, stretched, reddened, and delayed, until seeing turns into inference and inference turns into philosophy. We met the singularity as a warning label in the equations, a place where general relativity stops giving answers, and where quantum ideas, entropy, Hawking radiation, holography, islands, complementarity or firewalls, argue over what the interior even means. We also left cosmic censorship deliberately unresolved, because the universe has not yet told us whether it always hides its deepest failures behind horizons, or sometimes lets them leak into view. Callback. So what is the biggest black hole we can meaningfully talk about? And what does finding it do to everything we think we know about reality? The honest answer is that biggest is not a single number. It is a choice of meaning, and the best candidate is the one our methods can justify without pretending inference is sight. If we choose mass, we chase the heaviest space-time geometry we can constrain. If we choose horizon size, we translate that mass into a boundary measured in kilometers per sun. If we choose influence, we ask how far a galaxy's history bends around one dark center. If we choose power, we measure the light and jets of matter still outside, paying the universe's energy bill in radiation. Final thought. The biggest black hole, then, is not only a record holder, it is a boundary where our everyday ideas of time, space, and information begin to fail, and where the universe quietly invites us to rewrite the rules. And maybe that is the final twist of the journey. The closer we get to the largest darkness we can name, the more clearly we see that the real frontier is not the whole, but the limits of knowing. Call to action. Keep watching the sky through sharper interferometers, longer monitoring campaigns, and cleaner gravitational wave catalogues, because the next biggest discovery may be less a trophy and more a clue. So what is the biggest black hole we can meaningfully talk about, and what does finding it do to everything we think we know about reality? The honest answer is that biggest is not a single number, it is a choice of meaning, and the best candidate is the one our methods can justify without pretending inference is sight. The biggest black hole, then, is not only a record holder, it is a boundary where our everyday ideas of time, space, and information begin to fail, and where the universe quietly invites us to rewrite the rules. And maybe that is the final twist of the journey. The closer we get to the largest darkness we can name, the more clearly we see that the real frontier is not the whole, but the limits of knowing. Keep watching the sky through sharper interferometers, longer monitoring campaigns, and cleaner gravitational wave catalogues, because the next biggest discovery may be less a trophy and more a clue.